The delay. Live! And then we start the show. And we go, go, go. It is the thing. Yes, identity 4. Launch the missiles. Ready. Ready to go. I'm waiting for my cue that I know we are going to begin. Here we go. It's live. Starting in 3, 2. This is TWIS. This Week in Science, episode number 749, recorded on Wednesday, December 4th, 2019. How did it start? Hey everyone, I'm Dr. Kiki, and tonight we are going to fill your head with shrinky dinks, scaredy cats, and a bang. But first.
Disclaimer, disclaimer, disclaimer. The universe is a very big place, partly due to the fact that we only know of one universe, and compared to anything in it, the universe is always substantially larger. So, when pondering the universe, the first question that confronts a potential ponderer is just where to begin one's pondering. There are more than several logical pondering places to begin. However, for it always is recommendable to begin in a place immediately relevant to the ponderer. Being that you are most likely a hairless ape, you might start with pondering how a mostly hairless ape with such pondering powers came to be in the first place. And like loose threads of a tightly knitted sweater, this starting point will begin to unravel the recent development of human evolution on Earth. If you can avoid the detailed rabbit hole of human history, all the gnashing of teeth, flag waving, and near constant battles over this or that square measure of dirt, then you might get on to pondering all life on Earth. And even the Earth itself. Pointing your pondering beyond this planet will provide you with many more worlds to explore. The solar system. Beyond that, as if that were not enough, billions more solar systems are waiting to be explored in just this one tiny galaxy. And there are billions more galaxies beyond this one. And with all the galaxies and all the universe confidently in the pondering path, we must consider that matter makes up less than 4% of this stuff that is in our universe. And since the practice of pondering can propagate itself prolifically, it is probably more practical to simply apply that recommendation of pondering the immediately relevant. And there has never been anything more immediately relevant than This Week in Science, coming up next.
I've got the kind of mind that can't get enough. I want to learn everything. I want to fill it all up with new discoveries that happen every day of the week. There's only one place to go to find the knowledge I seek. I want to know what's happening. What's happening? What's happening this week in science? What's happening? What's happening? What's happening this week in science?
Good science to you, Kiki and Blair.
And a good science to you too, Justin, Blair, and everyone out there. Welcome to another episode of This Week in Science. We're back. We are back. We took a little break last week. We had a few mishaps and missteps, but you know, the show will always keep going. And so we're back and we're so glad to be here. And we hope you had a wonderful Thanksgiving if you are in the United States and celebrate that sort of thing. But we also hope that you had some science-y time in between these episodes. Okay, what do we have in store for you today? We have much science. I brought stories about shrinking things, birds and brains. They're shrinking. We're going to talk about that. I also have a couple of stories about domestication. And we have an interview tonight with a real live astrophysicist.
What?
Yes, real live on the show tonight. Yes. But we will get to that interview with Ethan Siegel in just a moment. Justin, what do you have for us on the show tonight?
I have got talkative bacteria, a couple of foggy ideas, and the EPA is under attack from the EPA. Right.
Attack from within. This is cunning. I like it. Okay.
From inside the house.
Yes. I'm inside the house. Blair, what is in the animal corner?
The Blair's Animal Corner tonight is for the birds. I have 2 stories about birds. One really good news, one maybe not so good. And then also I just have a little bit of news about a frozen puppy.
Oh, I thought for a second you were going to start talking about that Disney movie sequel.
No,
Not that.
this is a little less heartwarming.
Oh,
No, this is a wonderful story. I like this story.
It is, but it's, it's still a dead dog and ice.
all right.
Not really fun for the whole family.
And on that note, let's totally jump into the show. Fun for the whole family.
Yeah!
I want to remind everyone, if you have not yet subscribed to the This Week in Science podcast, you can find us all places podcasts are found: Google, Apple, Stitcher, Spreaker, Spotify, Pandora, TuneIn, radio.com, all the places. Go look for This Week in Science. You can also find the show on Facebook and on YouTube. You can find information about the show and show notes and all that kind of stuff also at TWIS.org, TWIS.org, where you can find information about purchasing the 2020 Blair's Animal Corner calendar. I have them in hand.
Have it.
I do. And we'll be mailing them. Toot sweet. So, toot sweet. But now it is time for our interview. I'd love to introduce our guest, Dr. Ethan Siegel. He is an astrophysicist and a science writer. He writes regularly on the Starts With a Bang blog on the Forbes website, and he's also authored 2 books: Beyond the Galaxy, How Humanity Looked Beyond Our Milky Way and Discovered the Entire Universe. You look beyond your nose, there's an entire world out there. And Treknology, the science of Star Trek from Tricorders to warp drive. And from what I hear, he's currently working on a 3rd book. Ethan, welcome to the show.
Thank you, Kiki. It's my pleasure to be here, and welcome. Thanks for having me on This Week in Science.
You're welcome. I'm so glad that we were finally able to make this happen. Now, we have some science talk that started on Twitter this summer, and then there were intervening months, and we'll get to that talk in a little bit. But first, I'd love to introduce you, or have you introduce yourself a little bit more in depth to our audience. How did you end up studying astrophysics?
I mean, so I'd like to encourage everyone who takes maybe an unconventional path, because I feel like to all the young people out there, you're probably getting a lot of pressure from the world that you need to decide what you want to do and how you want to do it and the path you need to take from a very young age. And I would like to tell everyone out there that was something that I did many different times and changed direction many different times in my life. And you can still wind up being an astrophysicist doing whatever you want. When I was an undergraduate, I couldn't decide on what I wanted to specialize in. I wound up majoring in 3 different things. And after I graduated, I went and did none of them and wound up teaching high school. And while I was teaching high school, I didn't quite love it enough and decided, well, if I wanted to go learn anything that I wanted to learn, what would that be? And the answer was, well, I really would like to know, if I could know anything, I'd like to know what the universe is, what it's like, how it got to be this way, where it came from, and where it's headed in the far future. Little things,
Just those little questions. Right, yeah.
And I realized when I was looking into this is not something for poets or theologians or philosophers. This is science. This is specifically a branch of theoretical astrophysics called cosmology, and I could study it. And so I did. I went to graduate school and I went and studied it, and I got my PhD in it. And then I went and did research for a while. And while I was doing that, I decided, doing this research is not really what I want to be doing full time. Even though I love the research I did, I wasn't loving what I was doing. So I went and had another crisis and went and said, okay, well, I love communicating science. I love teaching science. I love sharing the stories of what we know and how we know it with the world. And so I went and became a professor for a while, but I also started science writing and communicating. And a few years ago, I stopped being a professor and went full bore into the world of science communication full time. And that's how I got to be where I am today. So a little bit unconventional, but also to all the other unconventional people out there listening to this, your path is not fully determined, no matter how old you are or where you've gotten or where you came from. Keep on going. Keep on having those crises when you discover that the path you're on isn't the right one for you, and you'll never be disappointed with where you end up.
That's wonderful advice. And I would add to that also, your path is your own. So it
right? is. If you had come to me, 12 years ago, 13 years ago, when I was finishing up graduate school and said, hey, Ethan, this is the job you're going to have in 2019, I would say, well, okay, but that job you're telling me about, it doesn't exist today. It doesn't exist right now. And so to anyone out there wondering, oh, what's my 10-year plan? It's possible that your 10-year plan involves getting a job, working in a field, having a career that doesn't exist today. So don't try and force it. Don't try to over-constrain yourself. Keep your mind open and your options open.
So, and there is something to this in a bigger picture, which is that we don't live in that world anymore, where you go to school for a thing and then you do that thing for the rest of your life. That was how people did stuff a couple generations ago. But most likely, people will have 4 or 5 different careers and have to retrain themselves each one of those times for the modern workforce going forward. But always pick something that you like to do. Like, and I love the fact that you got into something and were like, yeah, nope, that was fun. I'm off to something else. I love this because, you might think you want to be a doctor and then at some point realize, oh, God, I don't like being around sick people. Okay, so then you need to change what you're doing. If that's
well, and that's also why volunteering and internships are really important too, because you can try things out before you jump in with both feet. But I love that idea. I say that all the time when people ask me why I've done or haven't done something at some point. Like, well, I still could.
You still can. All right, so science questions now. Time for the quiz Ethan hour. No.
Ooh, that sounds challenging.
Yeah.
How acceptable is I don't know?
That's the best answer possible.
Well, hang on. No, I don't know, but if I were to guess, that's more acceptable right here. If I were to speculate, I don't really
All you
know,
listeners, you get ready with the fact check. I want to see the comments. Everything I get wrong, everything these 3 get wrong. I want to see it.
Oh, we have these people fact checking us all the time. So I was interested in this conversation that we had started. You got involved in this Twitter conversation about the Big Bang. And I had put a little pop quiz on Twitter saying, when did the universe start? With the Big Bang? With the Big Bang and then inflation? Or was it magical unicorns? Or some, I came up with a bunch of different options for people. And what it had come from was a study that we talked about here on the show that kind of boggled our mind. It was the idea that there was something before the Big Bang. And that, from the lay perspective of understanding what's the Big Bang, I had come from this understanding of the Big Bang is when everything started. And now I am very confused, and I would love to have this conversation and really lay out for our audience kind of what is the current understanding of the Big Bang.
Well, I'd like to first start by saying anyone who thinks like you do or did, or that the Big Bang is the beginning, that it's the birth of space and time, and it's where the entire universe came from. This is what the leading scientists in the field thought was the case for decades. Likely when the people who taught you science learned it, that was what they learned. And for the first, few decades of my life, that was what I learned too. But when I was, college student in the late 1990s, I started to learn that actually the leading scientists in the field haven't thought that since about the early 1980s.
So we are way behind on the messaging
almost
here.
40 years behind, and I know you teased that Ethan, aren't you writing a third book? Yeah, this is what that third book is about. So you went and made sure you hit the right topic. It's how did the universe begin? Is it with the Big Bang? No. And before we get into what happened before the Big Bang, let's talk about what you would think of as the Big Bang. When we look out at the universe today, one of the biggest discoveries of the 1920s, almost 100 years ago, was that you can look at distant galaxies. 1920s was when we discovered that those spirals and ellipticals in the sky, they actually are galaxies outside of the Milky Way unto themselves. So you go and you measure, okay, I can see individual stars in those galaxies, or I can see supernovae in those galaxies, or I can see whatever you want to go measure in those galaxies. That tells you how far away the galaxy is. And you learn that because of the way that brightness and distance are related. If you see like a bright light source and you say, oh, I know that this is a 100-watt bulb, then if I hold it farther away, you're going to see it get fainter and fainter and fainter. And you can tell me what its distance is based on the brightness you perceive if you know how bright it is intrinsically. So this is how we measure the distances to distant galaxies. But what we can also do is we can say, oh, you know what? This is interesting. The galaxy that was close by, its light is actually shifted. It's red shifted, which means that just like if you imagine this is the wavelength of light, is this certain distance here, as the universe expands, the wavelength of that light expands as it travels through the universe. So a galaxy that's 1 million light years away is going to have its light red shifted by the amount the universe expands over 1 million years. A galaxy whose light takes 1 billion years to travel to us, it's going to have that light redshift the amount that it redshifts in 1 billion years, and so on. So what we can see is, oh no, the farther away a galaxy is, the more it looks like the universe has expanded. And that's where we got this idea of the expanding universe. So you say, okay, well, here's our universe now. And as we go forward in time, the universe expands, expands, expands. So you say, okay, well, what if we went back in time? Well, it would get smaller and smaller and smaller and smaller, and at some finite point you can go all the way back to a singularity, the hottest, the densest, the earliest time, t = 0. There you go. Big Bang.
That was the singularity. Just a little. That was it. It's a little pop. It's not a big bang.
Artist's interpretation sonically of the Big Bang. Yeah, I've got a pop filter, so hopefully it wasn't too bad.
Yeah, no, everything was very, very small. It was actually
like the trumpet with the mute on it for the Big Bang.
Yeah, and would it also be like taking all of the stuff that's expanded out in the universe that's all distant from each other right now and taking all that stuff and smushing it into
the universe? So the universe wasn't just hotter and it wasn't just denser. It was really taking everything in the visible universe and compressing it into the original term that they used. I love this. They called it the primeval atom.
Ooh,
that was
I like
before
that.
They called it the Big Bang. They called it the primeval atom. Doesn't that sound a little more epic?
I like that one.
The name, the Big Bang, actually came from one of the Big Bang's detractors, someone who didn't believe in it. He was like, what's this hocus pocus Big Bang nonsense? I'm sorry, he was British. So, what about this hocus pocus Big Bang nonsense, old chap? I'm sure that's how he sounded. But no, it turns out if you were to say, hey, the Big Bang is what's happening, the Big Bang is where our cosmic origins are, then you would expect certain things to exist in our universe that don't. You would expect that there would be some variations in temperature when you looked that way versus that way, because these two regions, they haven't had time to talk to each other since the Big Bang. So something way over here and something way over here, they haven't had time to talk to each other. You wouldn't expect they would have exactly the same temperature. And yet anywhere we look in the universe, it has exactly the same leftover temperature to within like 29,999 parts in 30,000. It's really, really uniform. There's only these tiny, tiny variations. You would expect that if you got hotter and hotter and hotter, you would reach this point where you created these high energy relics from the early universe. But we don't have any. We went and looked for them and they don't exist. And you would expect that the universe could have any sort of spatial curvature as long as, as long as you had, well, okay, we have some amount of matter and we have some initial expansion rate and they're going to balance kind of. But we find that they balance perfectly, over billions and billions of years, which is crazy fine tuning. That means if you were to take the initial expansion rate and you were to take the initial energy density of the universe, you would find that they balanced each other to like 20 significant digits, which, this is fine. But as a scientist, you don't say, hey, all right, all those are nice coincidences, and that's our universe. Let's give up now and go home. That's not how you do it as a scientist. You say, okay, well, I'm not a big fan of these fine-tuning problems. It's sort of like when you see a big giant rock balanced on top of a spire, you think, okay, either someone put it there or something natural happened, like some crazy erosion process happened to create this. It didn't just spontaneously arise. It wasn't like there was a giant falling rock and it fell on the spire and it stayed there. That's not how it goes. That's kind of what a fine-tuning problem is. So we went and said, okay, if that's what we have going on, what we're going to do is we're going to say, what could have set this up? What could have created the Big Bang with these specific initial conditions? And that turns out to be where cosmic inflation comes from. So when we take the Big Bang and we're saying we're going to extrapolate backwards and backwards and backwards, you get back to some hot, dense state. And then at that very early time, some tiny fraction of a second before you would get to that singularity of t=0, you get cosmic inflation. You say, going back in time from that, we actually have this inflationary state where instead of matter and antimatter and radiation and all these particles, the energy in the universe is bound up into the fabric of space itself. And that causes to expand with certain specific properties. But one of the things it does is it stretches the universe flat so that the expansion rate and the energy density balance perfectly. And another thing that it does is it creates these quantum fluctuations during inflation that get stretched across the universe and give us the seeds for cosmic structure that we need, that give us the seeds for galaxies and clusters of galaxies and the enormous cosmic web. And that matches our observations. And it also gives us a universe where these different disconnected regions and all these different disconnected directions have the same properties, because when you had this exponential expansion from inflation, it went and took this region that was small and maybe disconnected, stretched it so big so the stuff we see today after inflation's ended and we've had the Big Bang, it has the same properties everywhere. And maybe most importantly, it says we don't see these leftover high energy relics that we would definitely expect in our universe, because inflation puts an upper limit on what the temperature of the universe ever could have been. That you have an energy associated with inflation. Inflation comes to an end and dumps that energy into particles, and now you've got the hot Big Bang. See, I gotcha.
Okay, so there was a point. There was a point maybe pre-inflation, but that's not the Big Bang. So we've got.
So this is tricky. If you want to get into that,
it's prehistory, and then that inflationary period, the hot Big Bang, and then expansion.
So do you want me to tell you something honest but also a little depressing? I bet you do.
I do.
Yeah.
You know it.
The only imprints from inflation that exist in our visible universe come from the final about 10 to the minus 32 seconds of inflation. That tiny, tiny last little bit of it that happens just before it ends and we get the Big Bang, that's the only part that leaves an observable signature on our universe. So when you say, oh, maybe something happened before inflation, I'll go, yup, maybe it did. Do you have any evidence or idea for how we could test what it was, because it could have been more inflation forever and ever, or it could have been inflation for just a tiny little bit of time, and it could have started from a singularity, or it could have started from a cyclical state, or it could have been eternal, or it could have been some fourth option that I'm not smart enough to think of. So yeah, it's really interesting that when we came up with the Big Bang and we got the observational evidence for it, we were like, that's what it is. That's the theory. That's where the universe came from. That's where it had its origin. You investigate a little deeper and you say, you know what? Only back to a certain point. And then you have inflation, and that's where our knowledge ends.
And that's when they give you the instructions to, or the directions to the philosophy department. It's like down the hall.
Right.
Go down there. You can come up with it. Turtles, whatever you need. It's down there.
Well, I'm not a big fan of ragging on philosophers, because philosophers and physicists have had a go at it lately. But I will say, when it comes to the beginning of the universe, I'd rather ask a physicist.
I would as well. But going back to the beginning of the universe, we can only see what is visible, and we can only see what is as far back as we can find. So, I mean, really, still, how much of this has evidence and how much of this is still speculation?
And this is a really great question, right? Because that's just it. It's if all you do is concoct a theory and say, oh, I've got a new idea and it could explain something the previous idea couldn't, that's not enough. That's not enough in science. For me, when I think about what it takes for a scientific theory to get accepted in the scientific community, when you already have a prevailing theory, I think it has to do three things. Three things. All right. The first thing it has to do is it has to reproduce all of the successes that the previous theory did. So if you want something that emulates all the successes of the Big Bang, it has to reproduce all the observables that match what the Big Bang predicted. That's like the first step. If your theory can't do that, you don't have a theory. Like, this is not going to work. The second thing it has to do is you have to go and take, okay, there are all these things that the Big Bang couldn't explain, or that my pre-existing theory couldn't explain. But this new theory I have, it's going to explain those things. It's going to both reproduce all of the Big Bang successes, all of the previous theory's successes, and it's going to explain these things that the other theory couldn't explain. Now that's good, but that's just the start. The real test comes with step 3. Step 3 is to say, I want your theory to go out and make new predictions that are different from the predictions of the old Big Bang. So go out, make those predictions, and tell me what you get. So has inflation done that? The answer is yes. The big thing I told you about is those quantum fluctuations that happen during inflation, how they seed large-scale structure. In principle, we could have had big fluctuations on large scales and small fluctuations on small scales. Or it could have been the other way. We could have had big fluctuations on small scales so that you'll get a lot of little star clusters, but not a lot of big, massive, giant galaxies or galaxy clusters. And so then you can say, okay, well, what does inflation predict? And it predicts fluctuations that are almost perfectly scale invariant. So you almost get the same magnitude fluctuations on these small scales as you do on these large scales. But it says it should be slightly tilted, where the large scales, the fluctuations are just slightly bigger. And the small scales, the fluctuations are just slightly smaller. So in physics, we say, okay, well, we've got to give us a number to measure, or a parameter to measure. And so in physics, we call this the scalar spectral index, which is a little n with a s as a subscript. Right? So we go and measure this with our experiments that measure the cosmic microwave background, the leftover glow from the Big Bang. They say, okay, if it were perfectly scale invariant, we would get this quantity ns equals 1. And if it were slightly tilted the way we said, where the larger scales have slightly bigger fluctuations than the smaller scales, then that quantity n sub s would be just a little bit less than 1. This was a prediction that was made in the early 1980s, and starting with the COBE satellite and then going on to the WMAP satellite and now the Planck satellite, we have measured n sub s, and it is Remember I said it has to be just a little bit less than 1. We've measured it, and it is 0.965. That's one of 4 confirmed predictions that inflation has made. And so when you do that, when you have a prediction that's different from what the theory makes, and then you go out and you make the observations, and you're like, okay, I've got 6 things to measure. 2 of them I haven't gotten good enough to measure yet, but 4 of them I've gotten good enough to measure, and all 4 of them agree with inflation and not the old Big Bang with no inflation. I think you're doing pretty good. I think as long as you don't have a dogmatic prejudice against inflation, that you would absolutely say as a scientist, oh, well, you do everything that I want you to do. You reproduce the successes of the Big Bang. You explain the things the Big Bang couldn't predict. And then you went and you made a bunch of new predictions that we could test up against the predictions of the Big Bang. And the new theory wins every time. What more could you ask for?
Yeah, there's always kind of this resistance, though, right? When there's a new theory in town. I had a professor in college who made some brash claim that dinosaurs were closer related to birds than to reptiles, and was laughed out of lecture halls and all this kind of stuff. And it's, we hear this story time and time again, that you have this you have the traditional thinking, and it fits all the boxes that you want. But then if you have a new theory that fits some more boxes too, then it starts to kind of raise eyebrows, and there is a hesitance of like, well, but then we've been doing it wrong this whole time. That can't be it. But that's what makes science so amazing.
I mean, for me, I think that the idea that we're doing it wrong is itself a wrong-headed thing, because I hope that, people who grow up 200 years from now, they look at all the things that we say today about physics, astronomy, the universe, the same way we look at like all the things that like Galileo and Kepler were saying about the universe. Like, yeah, you got some great things right. Good on you. Also, your science is hundreds of years old, super out of date. We have much better science now, but you didn't do anything wrong. You moved the needle forward to from where it was when you started out. And that's incredible.
Yeah, Gregor Mendel didn't even know about DNA, but he was able to figure out how heredity worked, right? That's so amazing.
And biology is a great example, right? Evolution, Darwin's evolution was an enormous leap forward in terms of identifying how evolution worked and what the mechanism was by which evolution worked. But Darwin didn't know about genetics. But then Mendel came along and Mendel's successors, and lo and behold, hey, you know what? Now we've got an even better mechanism for how inherited traits works and inheritance, because genetics is a mechanism that underlies evolution. And then you discover DNA and you say, oh, and that's what explains genetics. So it's not like, oh, Darwin, he's an idiot because he didn't find DNA. I would love to read that book, by the way.
No.
But no, it's about advancing incrementally and literally standing on the shoulders of the giants who came before you to see farther than they could. We would not be where we are in terms of our understanding of the universe if we didn't have Einstein's general theory of relativity to build it out of. We wouldn't have the picture of the universe we do if we didn't have the last century's worth of astronomical and astrophysical observations. So all of this, it required an enormous amount of work by an enormous amount of people, some of whose names you know and some of whose names you don't know. But all of their contributions were important, and I think that's an important thing to remember too.
So in that though, there's something the bar set too high for coming up with a new theory, where you have to have all of these things in place, plus a prediction that doesn't refute the old but adds new predictions, because we have built all of this off people who had one small part of the puzzle figured out and everything else wrong.
I mean, you're welcome as a scientist, as a theorist, and I'm a theorist, so I'm familiar with this. You're always welcome to play in the sandbox. Right? You're always welcome to go and say, I'm not going to worry about reproducing all the successes of the Big Bang. I'm just going to worry about this one problem that I'm interested in and see if I can cook something up to solve this one problem. And you can do that. That's called building a toy model. And it's like step -50 on coming up with a new theory. And that's just fine.
Yeah.
But I wish that when you did that, when you were at step -50 over there, that you didn't sell this as I've got a new theory and it's replacing the Big Bang. And not
Totally
you
agree with that.
but everyone out there. So to those of you who are listening to the show right now, who are watching the show, when you see these crazy new headlines out there saying that like, oh, this proves that this crazy theory is right and this old theory that everyone had is wrong, you know, ask yourself that, like, hey, did you do those 3 massive steps that Ethan said you have to do? Did you reproduce the old successes of the theory? Did you solve the problems that the old theory couldn't solve? And did you make new predictions that we're going to be able to tell apart? If you didn't do that, it doesn't mean you did bad science. It means you did baby step science.
Right.
And that's okay. That's what most science is.
Because it's only because they didn't finish the headline, though. You know, new theory proves the Big Bang didn't exist, and also that gravity isn't a thing. Oh, wait, no, we have that. Yeah. We know gravity's here.
You could look at some of the stories that are out this week where I see people reporting like, could dark energy not exist? And the answer is yes. If you look at the data and you don't want dark energy to exist, you can absolutely look at that one piece of data and say dark energy doesn't exist. But also, if you look at only that one piece of data and you want dark energy not to exist, you need to build a universe that doesn't have any matter in it.
We matter. We totally matter.
That's the rest of the story.
Yeah. In terms of like ideas like this that have come out recently, there was a study that came out about our universe potentially potentially curved instead of flat, based on
I saw that one.
A reanalysis of some data. Did you take a look at that? And do you have any thoughts on like this is one reanalysis. It's one data set. I mean, it's going to be up against a lot of controversy, competition, discussion.
Well, if anyone read that or came across it, I can assure you that is wrong. But why it's wrong is interesting. And that's where, if you want to actually learn something about it, we can look at this. I don't know how many of you have seen those pictures from either COBE or WMAP or Planck of the fluctuations, the temperature fluctuations in the cosmic microwave background, right? You have these big maps and they show them with like red spots and green and yellows and blues, and some of them are hotter and some of them are colder. And what they correspond to is these density fluctuations in the early universe. Now, the thing is, the size of these fluctuations as they appear, they will tell you what the curvature of the universe is, because you can imagine taking a flat piece of paper and drawing a triangle on it, right? You draw a triangle on your piece of paper. And what happens? You add up the internal angles of your triangle and you get 180 degrees. But if your piece of paper was curved, you wouldn't. If you take a globe and you draw a triangle on the globe, you're going to find every time, no matter how big or what orientation you draw that triangle in, its angles will add up to more than 180 degrees. If you took a horse's saddle, something that curves in one direction upwards and in the opposite perpendicular direction downwards, that is an example of negative curvature. If you draw a triangle on that, you're going to get less than 180 degrees anywhere you draw that triangle. So when we look at these temperature fluctuations, like from the Planck satellite, we see they come in a particular size, with particular shapes, with particular patterns. If the universe were either positively or negatively curved, those patterns of fluctuations would look different than if the universe were spatially flat. Now, what this team did was they didn't look at that exact signal. They said, okay, well, the Planck satellite looked at that and it got this data and it got this constraint, but we're going to look at a different signal that comes from that. We're going to look at a signal that comes from what we call the lensing amplitude. The lensing amplitude is when you have a distant object, like this light from the leftover glow of the Big Bang, and it comes towards you, you're going to see the effects of all the gravitational masses in the way along your line of sight as the light travels to you. And when they do that, they said, ooh, look at what we're getting. The universe looks like it's curved. But why? Why does the universe looks like it curves? It's because, you remember I told you you're going to get this pattern of temperature fluctuations? Well, that pattern is not unique. That pattern is what we call degenerate. And degenerate means there are a number of different parameters that will all give the same answers. You can say, oh, okay, so we could have a universe with this much dark matter, this much dark energy, this much normal matter, this much curvature, and this expansion rate. So we could take these different parameters and we can vary them. So you can say, oh, well, maybe if we had more dark energy and less dark matter and more spatial curvature and a smaller Hubble constant, we could get that same pattern. And you can. And it's pretty interesting that the person who I learned this from was Alessandro Melchiori, who is a scientist from Italy who this is what he studies. I think this is maybe his biggest contribution career-wise to astrophysics. And I've been using this for almost 20 years. I've been using his research to explain that. Guess who was the corresponding author on the new paper saying, hey, you could change these parameters around and find a universe that had this positive curvature and it's closed at like the 4 or 5% level. Same dude, because that's what he does and that's how he thinks, and that's okay. But the thing is, you have to look at the other parameters, because it's not just, oh, we have the Planck satellite and that's our data set. You also have the large scale structure of the universe, which tells you actually the spatial curvature has to be a factor of 10 or more less than what he claims it is. You have the expanding universe, and you say, how fast is the universe expanding? And the answer he has to get, which is some value like 54, is way ruled out. There was a controversy about that where some people are saying, oh, it's closer to 67, and some people are saying, oh, it's closer to 73. 54 is no good. So without worrying about that, I would say you can safely dismiss that. But it's important to keep in mind that when we talk about how much dark matter, how much dark energy, how much normal matter, what's the expansion rate, there is some uncertainty there. There is some wiggle room, but you can't just wiggle anything the way you want it. These things move together. And that's the important thing, is no matter what you come away with, you have to fit the full suite of data, not just that one little piece of data that you want to get your preferred conclusion.
Right. Yeah. To fit the entire model or to change an entire model, you have to fit everything and add something new, or you're, like you said, you just have a toy model.
Did I satisfactorily answer that for you?
Thank you.
Did I sufficiently put the right people on blast for that?
Yes.
Am I announcing to the world that I'm 41 years old by using the term on blast?
No, not at all. No, it's good. You mentioned, though, so at dinner tonight, I was talking with my husband, and the idea, the question of, oh, how much stuff is in the universe that we can see, that, that's visible, or that's the baryonic matter. And he was thinking it was a really large amount. And I looked at him and I said, 4%. And he said, wait, what? I said, yeah, it's like, what is it? Like 26% dark matter, 70% dark energy. But this is all stuff that we can't see, we can't detect. I mean, where are we in figuring out 96% of the universe?
Well, that's a good question, right? Because when you say that we can't detect, there's two ways you can detect something. You can either detect it directly, which is what we think about when we say detect, where it's like, okay, I want to like hold it and feel it and make it in the lab and measure it and detect its properties. And that's the preferred way to do it, but you don't always have that option. That's not something that you can say like, I want to know how much energy is inherent to empty space itself. Let me just go find some empty space and measure it.
I have some here.
Oh, you do? That's great. How are you going to measure it? No, you don't have to answer. You don't have to answer.
And what is space exactly?
That's
Gonna
a whole
measure it in
separate.
increments of
That's a
time.
whole separate episode of This Week in Science.
I know it's a little nest. I was poking it.
When we ask questions like that, it's important to remember that we also have indirect methods, and this is often how we find things. Even if we can't know everything about them, we can still know plenty of things about them. So that's where we have this overwhelming amount of evidence for dark matter. You can say, okay, I have all these different galaxies and thousands of them bound together in this massive cluster of galaxies called the Coma cluster. There's like 2,000 or 3,000 giant galaxies in there. And we can measure how fast these galaxies are zipping around inside the cluster. If all we had was the normal matter from the stars, from the gas, from the dust, from the plasma, from the stuff we can measure, the normal matter in there, then all of these galaxies zipping around are moving too fast to actually be gravitationally bound. This cluster would fly apart if we watched it. In fact, every galaxy cluster that we found would fly apart. That is not what the universe is doing, though. We don't see galaxy clusters in the act of flying apart, so something has to be holding it together. And you were like, oh, come on, Ethan, like, when did they make that measurement? And I would tell you 1933. And you'd be like, what? Well, how come no one took dark matter seriously for 40 years? And it's exactly that phenomenon that you and Blair were describing earlier, is like, I have this old theory and I don't want to let it go. I don't want to let go. So maybe we don't need dark matter. Maybe there's more black holes or more planets or more plasma or more dust out there. Well, we build up a big suite of evidence. We looked at individual galaxies that are rotating. We looked at pairs of galaxies that are interacting. We look at the lensing signal that bends the background space behind it. We look at colliding galaxy clusters, and we see that the gas from inside the galaxy cluster clumps and sticks together while the mass signal passes right through and exhibits a lensing signal where the gas isn't. All of these things are very strong indicators individually that there's more to the universe than just the normal matter that we see. But what's remarkable to me is that every one of these observations points to the same amount more than the normal matter we see. They all point to about a 5-to-1 ratio of dark matter to normal matter. So if dark matter is about 27% is the best figure we have, the normal matter is only about 5%, and dark energy is the remaining about 68%. So that's how we get it, but we do it by looking at the full suite of data we have about the universe from all the different sources combined. If we didn't do that, I feel like we'd be shortchanging ourselves scientifically. And so even if you don't like the conclusion that's reached, it's not up to nature to conform to our prejudices about what it should look like.
Yeah.
But aren't we doing that a little bit? Aren't we using a prejudice by calling it matter? By naming it dark matter, we have prejudiced it to be a stuff because it has influence. Is it just because it influences gravity that we've called it a matter, like an unseen form of matter? But aren't we sort of pinning it down to being another billiard ball sort of particle-based thing that we would eventually get down to?
I mean, it doesn't have to be. It could be a fluid. It could be a field. But if it is a fluid or a field, there are certain things it has to do that, of all the things in the universe that we can theoretically concoct, they all behave like matter. So one of the things we can say is that this stuff, whatever it is, it has an energy density. It has an energy density that dilutes the same way that normal matter dilutes as the universe expands, which means if you make your universe twice as big, then the density of the stuff becomes 1/8 of what it was, because twice as big means twice in this dimension, twice in this dimension, twice in this dimension. So it's 8 times the volume. its density drops to 1/8. That's how dark matter evolves. That's how normal matter evolves. That is not how radiation evolves. That is not how cosmic strings evolve. That is not how dark energy evolves.
So it's
you
not
can
a misnomer.
say
It's actually a
energy
pretty
density.
accurate then description of this placeholder phenomena.
Well,
That it is behaving
that's
like
what I'm
matter.
trying to impress on you is the reason we call it dark matter is because it behaves like matter. It gravitates, it clumps together, it makes clusters. The overdense regions attract the normal and dark matter from the underdense regions. This works for dark matter, this works for normal matter. What dark matter doesn't do, normal matter interacts through nuclear forces and electromagnetic forces as well. If I take one thing of normal matter and another thing of normal matter and I smash them together, they're going to splat. If I take dark matter and I take dark matter and I go to smash them together, they just pass right through.
Right.
Camera
So
trick.
do we not have?
No
We don't have like
interaction. Yep.
clumps that we've identified of dark matter just hanging out by themselves. Like there's no dark matter source or galaxy out there that we've been like, okay.
Well, the problem is matter gravitates. Normal matter, dark matter, it all gravitates. What we do see, though, is if you take a clump and you let it collapse, if it's normal matter and dark matter combined, the normal matter will splat, form stars, heat up. And then once you form stars, it makes this outward radiation pressure. That radiation pressure from winds, from photons, from cataclysmic events, it can eject the normal matter. It can put a pressure on the normal matter, but not on the dark matter, because the dark matter doesn't feel those forces. So what we expect to happen if dark matter is real is that we will see this 5-to-1 dark matter to normal matter ratio in the big cosmic structures. But if we start looking at itty bitty galaxies, tinier and tinier and tinier, we expect to start seeing much bigger ratios because the dark matter stays in the clumps, but the normal matter gets ejected. The smallest galaxy I know of is called Segue 3, SEGUE 3. And it has a dark matter to normal matter ratio of about 600-to-1.
Wow.
So
Is this
again,
thing
I would
moving?
say it sure is acting the way we expect matter to behave, but matter that doesn't interact through the electromagnetic or nuclear force.
Right. Fascinating. So I know this has been such a wonderful almost hour of conversation that's going by much too quickly.
Oh my gosh.
We have a couple of questions from our chat room with relation to black holes. And so I know that is another topic. Do you have time for one or two more questions?
Yeah, let's take some of the questions from the live comments. I see we've got a few YouTube comments that that have some things to say. So which ones would you like us to take on?
So I love the question of the idea of black holes versus white holes. The Singing Saw guy asks, is there any theory that supposes there's a parallel negative or positive universe next to our positive negative universe, and that black holes here are stars there, and vice versa? Black holes there would be stars here.
You know, there is a theory about what black holes in this universe do as far as making another universe, but it isn't that a black hole here is a white hole there or a star there. It's that a black hole here in our universe is actually a gateway to another universe. That when you go and fall into a black hole, you actually come out the other side sort of like you would similar to a Big Bang here. So that there's that same idea that when we make a black hole, that is a gateway to another universe with a different mass, maybe a different set of constants. But that's the beginning of that. And maybe, just maybe, our observable universe, you know, although we say like, okay, either inflation or something identical observation-wise to inflation happened, maybe that actually came from a previous universe's black hole, that the spawning of that gave rise to us. So that's I would say the most compelling theory we have about the connection between black holes in our universe and other universes. And that's still speculative, But that's a fun speculation to me. And
Yeah.
if you're at home and you're like, I want to learn more about that, Andrew Hamilton at University of Colorado has written some great papers about that. So go ahead and look them up. They're
Fantastic.
free on the archive.
Oh, fantastic. Yeah, and you're kind of alluding here to another person's comment or question about this commonality between the singularity in the primeval atom before the Big Bang and the singularity that's related to black holes. Is the math that describes that somewhat similar in this theory?
Well, it's really interesting when you look at general relativity, because what a singularity really means is it's a place where the physics of space and time break down.
Mm,
If you start looking at what was the Big Bang singularity like, well, we've already talked about why we don't think there was a singularity at the Big Bang, right? That idea that you can say, oh, yeah, we're going back, singularity. No, you go back, and then inflation. If you went and did the math on inflation, and you'll say, oh, well, surely, like, if inflation is expanding exponentially, then you can go back and everything will connect there. But that's not necessarily true. If you were to take an exponential, right, and you were to say, okay, exponential, it rises like that, but I go back and back and back and back in time. If I take something that's an exponential, like e to the something, to the variable,
right.
right? Those of you who are like thinking in math, right? E to the something. If I take something and I let it get very big, e to that thing is going to get really big. It's going to get real big, real fast. But if I go backwards, if I take e to the 0, I don't get 0, I get 1. And if I go back, e to some negative number, e to some really large negative number, I still never reach 0. I only asymptote towards 0. For those of you who don't know what an asymptote is, it's like paying back your student loans. Right?
Get closer.
Why do I still, I've been doing this. How old am I? Why? Why am I still paying back my student loans? That's a joke. But that's what happens, is there isn't necessarily a singularity for the Big Bang anymore. What I think is fascinating is if you are forming a black hole, if your black hole doesn't rotate, the singularity you form is going to be a point. But if your black hole does rotate, that singularity is no longer a point. It gets extended into a ring. So you actually get a Homer Simpson donut for your singularity.
Donuts. I love it. One last question here. We've who is this over here? Is Moth is curious if dark matter contributes to the creation of black holes.
That's a really good question, because dark matter is just like normal matter in the sense that it gravitates, but dark matter, because it doesn't splat like normal matter does, it doesn't have any good way to lose momentum and angular momentum. So dark matter exists in these enormous halos around galaxies that are very, I think the word I like to use to describe a dark matter halo is very fluffy. Right? Gabriel Iglesias would appreciate that, right? It's very fluffy in a dark matter halo, as opposed to these splat things. So you make a star, and the core implodes while the outer layer gets blown off. That's where you get your black hole from. The black hole arises from normal matter. But once you make that black hole, any matter that encounters its event horizon is going to get sucked in. So if you work through the math and you say, hey, you got like a supermassive black hole at the center of the Milky Way, it weighs like 4 million suns. How much of that comes from dark matter? And the answer is pretty substantial. It might be like 7 suns. 7 of those 4 million might be from dark matter. So it doesn't make black holes on its own, but the longer you wait, the more and more dark matter will fall into them.
Right. The stuff that's nearby and within the gravitational field.
Or give it enough time, then let the stuff that's not nearby come to you, because gravity has all the time in the world, maybe more.
Gravity, it's patient. It can wait.
On the longest time scales, I could argue it's the only force that really matters.
Yeah, really, truly. And it's one that we still have so much to figure out. We still there are people who say there's the graviton and there's a particle that we're going to find. We haven't found a particle. There are people that say it's just an emergent force. We don't know that either. We know it works.
That is a good example of a toy model. Just the one that it's an emergent force. But what I think is fascinating, if you want to actually wrap your head around why would we even need a quantum theory of gravity? You've heard of the double slit experiment where you fire an electron, even one at a time, through a double slit. That electron goes through, and somehow that electron is interfering with itself. And you measure one electron after another on the screen, and you see you've got like electrons and no electrons and electrons and no electrons, and you make this interference pattern. We do not have an answer to the question of what happens to the gravitational field of an electron as it goes through a double slit. We don't know how to answer that. That's one of the reasons that we need a quantum theory of gravity, because in general relativity, you don't get an answer. We don't know how to answer that. Yeah, and because, that I think is a beautiful, simple experiment that you can think of that illustrates why we need quantum gravity, even if we don't have a theory for what it is.
Yeah, because the bizarre thing about that double slit, isn't it, that even though these are being fired electrons one at a time, they're hitting that back detector as if they all went together at the same time and interfered with each other to create this pattern. So it's as if they ignored the fact that you took time intervals for your experiment, and light said, don't care about that time interval. I'm going to do this. I know what you're doing. Though it's all happened in the same instant. That's what's crazy about that experiment. Yeah, it's absolutely mind-boggling in the timey-wimey, wibbly-wobbly sense of linear time being a thing.
Yeah, and another author, Anil Ananthaswamy, has written a wonderful book about the history of the double slit experiment, and we interviewed him on a previous episode. Oh my goodness, Ethan, it has been just amazing talking with you tonight. Thank you so much for your time.
It's been my pleasure. Thanks for having me on the show, and thanks for all the challenging questions and the interesting lines of conversation that we've had.
It was wonderful.
I still feel like we didn't have enough time.
We didn't have enough time.
We went way over time. And we didn't even get into the science of Star Trek stuff. So
we didn't even get into the science of Star Trek. Spock would like you to live long and prosper.
Okay.
Where can people find you online if they would like to continue following your writing and your scientific thought escapades?
Well, so I'm Starts With a Bang, which means if you look up Starts With a Bang on Forbes, you can find all my latest writing there. I'm also on Patreon at Starts With a Bang. I'm also on Twitter at Starts With a Bang. I'm on Facebook. And for those of you who like podcasts, I also have a podcast on SoundCloud and in the iTunes stores called the Starts With a Bang podcast. Yeah. Surprise.
Starts with a hot bang, but really inflation.
Yeah.
That's what we learned tonight.
So our observable universe, the way we know it, started at the end of inflation with the start of the hot Big Bang. But that doesn't mean the Big Bang was the very beginning of everything.
So I learned we know some things, we don't know some things, and there are things that we think we know that later we'll learn we don't know all about.
I think that's probably fair. I would agree with all of that.
Isn't that always the state of everything, though? Yeah. Blair? Wait, were you doing like a Captain Obvious thing there, Blair?
Yes.
Wait, what happened?
I think you got halfway to Donald Rumsfeld with that one. Now tell me about the unknown unknowns.
Unknowns that we know we don't know.
My unknown knowns, my unknown unknowns. Yes. All right. Thank you so much for joining us tonight. If you would like to stick with us for the second half of the show, we have a lot more science to come. We're going to take a quick break. I have some things to tell our audience about. But if not, I will say adieu. What do you want to do? We will say goodnight. Thank you once again. Have a wonderful, wonderful week.
You too.
This is This Week in Science. We are going to take a quick break and come back, like I said, with more science. We have shrinky things, birdie things, domestication, and other things coming up in the second half of This Week in Science.
Can't explain things you've heard with more than intuition.
Thank you for listening to This Week in Science this week. Guess what I have? I have the TWIS 2020 Blair's Animal Corner calendars. The crowd goes wild. They are beautiful, full of amazing original artwork by Blair and science holidays that you can enjoy and appreciate all year long. Things like Squirrel Appreciation Day. How about International Zebra Day, Darwin Day, Galileo Galilei's birthday, which is also the same as National Hippo Day? You'd know that if you got a TWIS calendar. Go to twis.org right now. Get yourself a calendar. Buy one for a friend. I'm going to be mailing these very soon. If you don't have one, what is your 2020 going to be like? Oh, just sad. You should find one of these calendars by ordering it. That's right. It's got contact information for us. Tells you about the TWIS. Tells you beautiful animals of art. And, you know, if you wanted one of these original artworks, you could become a patron on Patreon. And at one of the levels, we send you original artwork from Blair. That's right. These original pieces of art that went into making this, you could have one and hang it on your walls next to the calendar that you buy. That's right. Patreon really is the thing that keeps us going all year long, month after month. Your support really helps. The calendar is wonderful, and it's a reminder of all the good twissiness throughout the year, and it does support us also. And it's, I mean, Blair puts a lot of heart and soul into this thing. She really does. So I do hope that I see your orders coming through now, right now. I want to see that. You know, This Week in Science, we're here because of you. Thank you so much for your support. Can't do it without you.
Can't explain things you've heard with more than intuition. A lot of research shows the way to go.
And we're back. You're listening to This Week in Science.
This is This Week in Science. Oh, yeah. And it's time once again for the segment that comes after the break. You know what it is. This weekend, what has science done for me lately?
Getting better every time.
You know you love it. Alrighty, everyone. Our letter this week comes in from a longtime listener. She writes, "This email is long overdue. I've listened for years and have had comments that go as far back as KDVS, the revolving door of interns, and the near crossover with This Week in Tech. While this trip down memory lane is brought to us by my hippocampus, science has helped me remember those small tasks that are often forgotten, but not anymore. Science has given us computing, and modern usage has given us digital assistants. With a wee babe on my hip, I have mastered the art of remembering tasks when appropriate, like remembering to buy donuts. Donuts, yes. After dinner when the shops are closed. But now when I remember something at a bad time, I can tell my watch to remind me, and I have now fooled people into thinking that I actually remember more than I do. Thanks to science, I can say, hey, digital assistant, remind me to buy donuts tomorrow at 7 a.m. or remind me to email Kiki tonight at 10 p.m. What a difference one sentence can make when I can actually respond to my own calls to action. Thank you, science, for helping me be a responsible adult. Thank you, Kirsten, Justin, and Shouty Blair for being my long-distance friends. Apologies for being in the shadows for so long. I would only remember to write in when I was driving and unable to write. Lisai, yours, Tracy.
Thank you,
Thank
Tracy.
you.
Thanks, Tracy.
Yeah, I'm glad that that science helps you be a responsible adult and that we are your friends. We're your science friends. Yay. Thanks for being with us for so long. I love that you've been listening to us since the early KDVS days. And thank you for finding a way to remind yourself to write in. Science, technology.
Man, I do that all the time. I just, on Monday, I set an alarm that said, remember to collect fecal sample for the vet. And then I had another one that said, remember to grab poop from fridge. And I would not have showed up with that at the vet if it weren't for those reminders.
Oh, and
Thanks, science.
I like that you had to say, remind yourself whose fecal sample.
Come on, it didn't say that. It said sadie poop was the reminder. Oh,
sometimes you only need 2 words.
Yeah.
Sometimes
I was supposed to bring my dog's fecal. I'm sorry. I left a note. It was not obviously explicit enough.
Would that be a poop oops? Okay. Anyway, everyone, if you're watching right now and you're like thinking to yourself, "Oh, yeah, I'm not in a place where I can write in, but I'd love to do one of these this week and one of these this weekend. What has science done for me lately?" Tell your digital assistant right now. Send Kiki an email at kirsten@thisweekinscience.com or send a Facebook message to the This Week in Science Facebook page. Mm-hmm. Yes, digital assistant. Oh, maybe I can turn on people's assistants right now. Hey, Google Assistant, send Kirsten an email. I don't know if that's going to work.
Then you also have to get Alexa and Siri too.
I do.
Yeah. It'd be kind of interesting. And this is more planning than this. It would be quiet. But I would be interested in doing one of those things where we sort of had what has science done for me lately in a poll form where we ask a question like, what piece of technology do you most benefit from in your daily life? And just have like one sentence answer from, a couple dozen people and sort of run through what is it? What is technology? What do you most viscerally? I mean, I get a lot of it will be a phone because we.
But it would be neat to see the things that come.
But yes,
right?
But why? How do you use it, or what is the application?
For me, it's the maps.
The what? Oh, maps!
Maps.
Oh, that's a fantastic
navigation.
One. Yeah, such a now.
Thanks, satellite.
Thing.
Thanks, guys.
Yeah. It's such a given thing that when occasionally traveling with a beyond reception range on a phone, I will now I'm off the map. Now I'm in unexplored territory.
Which direction am I going? North, south? I don't know.
I don't know where I am. I'm off the map, everybody.
Some sort of way. I need to go find a tree that has moss on it to figure out where north is. There's some other method of where's the sun? I need the angle of what time is it? And then I can, yes.
Do you know what time it is right now?
Time for science news?
Time for some science news. It is. Yes. We've got some news for you. Oh. Apparently, researchers looked at the brains of scientists who have spent time down in Antarctica. Because, hey, why not? I mean, you're going to go hang out in this fairly homogeneous environment where everything in the landscape is white and there's not a lot of stuff that's different from the ice that you see. There's not a lot of variation, and they're isolated. They don't interact with a lot of people. So the social circles they're interacting with much smaller. So the researchers, they just published their results of a study looking at the brains of these researchers. They say on average, the hippocampus of the brains of these crew members, these team members, shrank by 7% over the course of one Antarctic expedition.
What?
Yeah, so there's brain shrinkage. And this area, the hippocampus, if you've listened to the show, you'll know it's one of my favorites. I studied it when I was a grad student. Hippocampus, it's related to learning and memory. It's also related to navigation. And we have seen reductions in size of the hippocampus in rats who have been in kind of deprived housing situations where they've been not around other rats, where they're isolated, where they don't have a lot of stuff to play with and keep them busy. When they are suddenly given what's called enrichment, with stuff to do and other rats to hang out with, their brains, the hippocampus, bursts into action, and there are new hippocampal brain cells born in the rat's brains. So the question is, why does this happen? Why does the hippocampus kind of start to atrophy? Why does it shrink? What is happening there? And does it really affect the memory of or the learning ability of these researchers, these people who are down there? And if that's happening in Antarctica, how would it affect people who are going to Mars, for instance? Right? Very interesting questions. But
Yeah.
it's not a significant 7%, not a significant size change, but it's interesting in itself.
So they're saying it's because of a reduction in sensory input, basically?
That's what they think. So the idea is because the environment is, I guess, deprived compared to the normal, especially if you're a scientist, you live in
boring.
Right. You live in an urban environment. There's lots of stuff around. Antarctica, there's not a lot of stuff.
So
And there's not a lot of people, and there's not a lot of stuff to do. Everybody sticks to a pretty rigorous schedule, and it's maybe potentially monotonous.
So I'm just thinking about the opposite end of the planet, the Arctic. There's lots of native peoples that have lived there and are from there.
Mm-hmm.
How do their hippocampuses look?
I don't know.
Because
I don't think anybody's ever
right?
done that.
Like,
yeah.
Is it because you're used to one thing and you're putting them in a space that is different, or is it just because I would also argue that as a person who's doing research, yes, you might not be doing that much. You brought your own food in, you're sitting in your tent, you're sorting through camera track photos or ice cores or whatever it is that you're doing, right? It's kind of very specific, but if you're trying to live off the land in an actually really brutal space, that's actually you're going to be engaged all the time. It's not boring.
So the first thing I thought of was these crews at least are going to be in a state, I would assume, of endless sun, where they don't have a dark time, they don't have a nighttime. So it could be a circadian rhythm type thing that gets involved there. But I think the lesson is if you're going to the Arctic, either bring a lot of books. In
the Arctic, but the Arctic also there are predators. There's a lot more going on animal-wise. There's still a lot happening in the Arctic compared to the Antarctic. And the interesting thing of this is they have.
Well, as Kiki freezes for a sec, it's more active. But I'm also the other thing I was thinking of then would be like if we go back to early man, are we talking about not having as many other humans around to interact with? Are we talking about the evolution of the hippocampus having to do with human interaction at that point. Is that a thing? Is that a portion of it? It's really fascinating though, that because we humans, we're not like actively interacting with the nature and the wildlife and the predators and the things that might be in one versus the other. So I don't quite feel like that would be enough to explain a difference.
Yeah. So I was going to say what they did is they looked at the brain's magnetic resonance imaging before and after the expedition. It was a crew of 8 scientists, researchers, and a cook. They lived and worked at the German research station Nummer 3 for 14 months. So they were there for the entire year, full summer, full winter.
Okay.
So while in the summer months, there were other individuals who came to enjoy the summer research opportunities in Antarctica. The winter, though, they were a very small crew of people enduring the darkness and the cold temperatures of Antarctica, which can be extremely unhospitable, and where you're stuck inside and not able to even go outside. And so there's social isolation in this scenario. And so they think it may be social isolation and monotony of the environment.
It could be that, yeah. I'm now curious, did they measure them after the dark period? Did they come back from like having been in 6 months of darkness? Because that would do it to me. That would absolutely be
not being able to go outside.
It's the worst possible version of seasonal effectiveness disorder, right?
Yeah.
Just you're the saddest person in the world. I just want to.
Yeah, another aspect of this is that knowing the hippocampus is partially involved in navigation, and if you have a monotonous environment and you're not exploring new spaces, there's nothing new, you know where everything is, your hippocampus is maybe just like, I don't need to make new connections. And your brain is plastic, right? We've talked about plasticity and how the brain is like, if I'm not using this, I'm going to use this energy somewhere else. I'm going to do this stuff other places. And so maybe the hippocampus saves resources.
And because it would very much limit what you were mapping if every time you looked out the window or went outside, it was just darkness everywhere. And darkness without anything like to even, like real darkness, like the darkness when you don't have any light pollution whatsoever.
Which
the
would
brain
be like
would
the darkness
need
of space.
not to map to nothing, basically.
Nothing
from your brain's perspective.
It sees nothing. Another interesting study out this week suggests that perhaps humanity, that as we speciated and became humans, that maybe we domesticated ourselves. Maybe there was some aspect of self-domestication that took place. Researchers looked at a gene called BAZ1B, and it has a role in the movements of neural crest cells. And there is an idea that neural crest cells, or at least a smaller number of them, that's linked to domesticity in animals. So they were looking at these neural crest cells, found this one gene that's involved, and most people have 2 copies of the gene. However, there are some individuals who have only 1 copy, and others it can be missing. And there's a genetic disorder called Williams-Burren syndrome, which has cognitive impairments and changes in facial features to become more elfin looking. Skulls are a little smaller. And there's also a proclivity to friendliness, being more friendly than usual. So they wanted to figure out whether or not BAZ1B was involved in the changes in the facial features. And so they played around with stem cell lines. They got stem cell lines from people with the Williams-Burren syndrome. They had stem cells from people with a related but different disorder where instead of missing the gene, they actually have duplications of the gene within the genome. And then they had copies or stem cells from people who didn't have any disorders and had the normal complement of 2 copies of the gene. Now, they turned BAS1B up and down. They were playing with how much it was expressed in these stem cell lines and then looked to see what other genes or proteins got expressed as a result. So what other genes, when BAS1B gets turned up or turned down, what happens to other gene expression and how do things change? And so they found that, yes, indeedy, when BAS1B is messed with, it affects the expression of genes that are related to facial features. And so they also looked at these genes, this one gene, in 2 Neanderthal genomes and 1 Denisovan. And they found that in modern humans, we have a whole bunch of regulatory mutations that come associated with BAS1B that are not there for Neanderthals and Denisovans. And so they think that people, because we were farming and we were living in groups, and maybe we had to be nicer to each other or find nicer mates or something, that maybe over time we domesticated ourselves, and the expression and regulation of genes like BAS1B is a hint of our domesticity.
Yeah. Hey, well, that makes absolute sense. Yeah. I mean, we have been livestock of society for a really long time. If you whatever, going back as far or recent as you like, if you didn't fit in with society, you became banished. So yeah, here's a pack. Go out into the wilderness. You're on your own now. Don't come back to the village. To modern day incarceration, to however far back you want to go. Humans have been filtering other humans in terms of their ability to play nice for a really, really, really long time. So yeah, social selection absolutely has got to be a driver, and that we could see it in a genetic level is pretty spectacular, actually.
I think it's very interesting. Now, the interesting question here, we've talked before about this domestication syndrome, and you've talked, Justin, about the trut foxes and this domestication experiment from Dmitry Belyaev in Russia, where he took a bunch of foxes and tamed them, and the foxes ended up having dog behaviors, and they were much more friendly, and their appearance changed. And they didn't really look at the genes involved in that. But now here's a study that's in Trends on Ecology and Evolution that argues that maybe what he says is domestication syndrome is not, and that maybe he started out with much more domestic foxes to begin with, and that perhaps all that they're looking at is just a directed breeding situation. And that they say our main point is not that domestication syndrome doesn't exist, but just that we don't think there is enough evidence to be confident it does exist. Yeah.
Interesting. So yeah, the fox study, when we say they were taming these foxes, basically they were just breeding ones that were less repulsed by humans with other ones that were less repulsed by humans, and over and over again through generations. And the ones who became the most, you could call it tamed, but it was tamed not by humans taking them in and being like, okay, now I'm petting you and feeding you and taking over these things. It was just by breeding the less sketchy ones around humans over and over again. Yeah, these more relaxed over time around human foxes did start to morphologically change, and part of it I think had attributed to in vitro hormones that more relaxed mothers have different colorations in their offspring. And it had to do with in vitro hormone changes that would then be reflected in different color patterns and fluffier ears and more like puppy-like stages being prolonged within the next generation of foxes. It's still such a very fascinating study.
It is fascinating. I think the interesting point that the new study that is saying, well, maybe they did see this in the foxes, but when they look at other animals and they look at this idea of attitude, I guess, of personality along with physical changes that accompany it, it's not consistent across different types of animals. So dogs, cats, the skeletal changes, the facial changes, the coat color changes, they don't all necessarily come together. And so they are wondering, based on the data, they're saying it just doesn't seem like there's a preponderance of evidence to really support this idea. So anyway, did humans domesticate ourselves and make ourselves friendlier and give ourselves nice big skulls and all that kind of stuff? Did our faces change because we domesticated ourselves? We found a gene that's going along, but maybe this domestication syndrome doesn't even really exist in the first place. So what do we think about that?
There's a pretty clear answer to this question, and that is just do it again.
Do it again.
Take some wild animals and see if in some generations you see some changes. Yep. Feel like you will.
Yeah.
Feel like you will. This is This Week in Science. Hey, Justin, tell me a story.
So this one has a link in the rundown with an awesome video, which if you're just listening audio, that you'll get along just fine with it. This is a story about bacteria, the beneficial cohabitants of human bodies that are, it's a life form that lives almost anywhere and absolutely everywhere that any form of life is found. There are only a few strains of bacteria that can cause problems for human health. They might, according to this study, pose a little greater threat than we might have thought, because it turns out bacteria can communicate with each other.
What do you mean by that?
But yeah, they can. They send chemical signals, right? Yeah. Mm-hmm. Right. We talk about quorum sensing and other stuff.
Yes. So this is bacteria Pseudomonas aeruginosa or something along those lines, notoriously infecting patients with lung disease, cystic fibrosis. And the study researchers found that the bacteria can send out warning signals to their fellow bacteria when attacked by an antibiotic virus, a bacteriophage. And in the video, if we can bring it up, what you'll see is they have put these, they have a petri dish, and in the middle, they have inoculated it with the bacteria. And they have a number of dots near the outside of the petri dish where they have this bacterial phage, this antibacterial. And as the bacteria spreads from the center, it simply grows everywhere around where that antibacterial is. Now, if you just look at it, it might look like, okay, it's getting killed there, and that's why there's no bacteria forming. But it's not. It's actually stopping, growing towards it, and going, something over here. Hey, everybody, when you see, let's just go around. And that is not something that we thought bacteria could do. Not just getting killed off by the antibacterial that's in this dish, but actively avoiding it. That's crazy. That is absolutely crazy.
How are they doing it? How are they doing it? What's going on?
That's the question. Yeah. Mm-hmm.
Cups with long strings. Hey guys, hey, avoid this area of the dish, would you?
Yeah, this is a Cordy voice of Nina Molen Hoyland Kogsbo. I'm saying your name terribly wrong. Who I think is at the University of Copenhagen. It is quite fascinating for us to see how bacteria communicate and change behavior in order for the entire bacterial population to survive. You can almost say that they act as one united organism. That's yeah. So
it's like slime mold.
Mm-hmm. Just like a slime mold.
Mm-hmm.
So this is new knowledge that then they can start to look at. But it also shows that using, what I sort of immediately pictured from this was you're using an antibacterial on your counter. So then anything that grows just grows along the cupboard or the wall instead. I mean,
or in the cracks.
It's not killing it off. It's just going to grow around what you've sprayed. But that's also, as we are getting into these phases of having to come up with more antibiotics and understanding how the biotic world works, knowing that they can actively avoid the countermeasures and not just
take evasive action.
So yeah. So I mean, this is not an antibacterial resistance that we have seen in this experiment. This is antibacterial avoidance.
Yeah.
That's a whole different thing. Yeah. Anyways.
Fascinating. That is fast. Why? I want to know. I want to know what they're thinking.
Yeah.
Tell me what's on there.
And so it's not in this study that I could see anywhere, but I keep thinking there has to be an event where one of these bacteria is destroyed by this antibacterial. And somehow, as if like an antibiotic signal going out to the rest, if encountering this sort of a signal, don't head in that direction.
Right.
I mean, there has to be something of this sort of mechanism taking place. But it is then we're also talking about as if an immune system of a larger organism, as if a genetic memory of some sort, or information passing throughout the colony to be aware of.
Yeah, well, we know that there is information that does get passed through bacterial colonies, and it's not just things like slime molds that do that kind of communication. It's been shown that that bacterial colonies will respond to food sources, that they'll grow toward food sources, that there is stuff that there's something going on in terms of communication.
Yeah, and also in times when there's not enough nutrients, those bacteria on the outside will continue to pass nutrients into the core of the colony, even as they themselves are not taking as much nutrition and maybe even starving. This is the sort of altruistic colony, as it was coined at the time. But there are survival strategies that the colony has that an individual bacteria would not be engaged in.
No.
Yeah.
Oh my goodness. Oh, bacteria, you're more complicated. You just keep getting more and more complicated. Wait. You know what else is complicated?
What?
Animals. Animals are complicated. And
the solar power.
It's time for Blair's Animal Corner.
With Blair.
She loves our creatures, great and small. Biped, millipede, no pet at all. You want to hear about animals? She's your girl. Except for giant pandas and squirrels. There's Animal Corner.
What you got, Blair?
There we go. I was like, I need that one last cue from Justin. So I have a really cool story about bird bones. So for a quick second, I just have to do a little bit of scaffolding here so that people understand how bird bones are special, let's say.
Them bones.
Birds can fly. We all wish we could fly. We can't fly. It all boils down to one thing. We're too darn heavy. Birds are light enough to fly for 3 reasons. 1, they're keeping warm with feathers instead of heavy hair. 2, they have a really fast metabolism and they poop a lot, so they're not weighed down by food. The third, very important, hollow bones. So if you ever have a chance to look at a bird bone, if you cut it open, it really is hollow. There's kind of these very thin bone structures that are almost like struts or scaffold in
Mhm.
the hollow bone. But if you cut open a mammal bone, it is dense and thick and solid. So this difference between our bones is why you could have a golden eagle that weighs 11 pounds and a golden retriever that is around the same size that weighs 80. So that is one of these big reasons that these birds are light enough to fly. The big downside to that is that when a bird bone breaks, it shatters. It's really hard to put back together or make heal again. And if it doesn't heal back exactly right, the ability to fly can be lost. Which brings me to the story that I brought tonight that I'm so excited about. This comes from the Shiraz University School of Veterinary Medicine's Department of Surgery in Iran. And they have tried something completely new. So in the past, if you even tried, a lot of the times, like most of the birds that are native birds that we have at my zoo, for example, most of those animals are unreleasable because the bone was so damaged when they were hit by a car or something else happened that they actually had to amputate the wing. So in most cases, bird bones are not even healable. But when in previous procedures that have worked in rehab situations, they actually put metal pins in the bones. Just like if you broke your bones really bad, you might get pins. Two problems there. One, then you have to catch the wild bird again to take the pin out, or you have to keep them so long that can impact their ability to live in the wild after rehab. But the second is that metal is heavy.
Mhm.
And so if you leave it in, then they have a really, really, really hard time being able to fly afterwards. This is imbalance in flight, takeoff, or landings after fracture repair. So in trying to figure out something new, they have found that you can use sheep or dog bones, so these dense mammal bones, whittle them into orthopedic pins, like those metal pins, to stabilize wings. And this is done on pigeons with fractured wings. That helps them heal properly without follow-up surgery. And the best part is that they become absorbed by the body. So it's cheaper, it's more effective. They don't have to be taken out afterwards. And because they're absorbed by the body, it doesn't impact their balance or their weight distribution. So it has so far worked really well in these pigeons. They're hoping that they could extrapolate this into other wild birds, eagles, owls, seagulls. These are animals that you see a lot in rehab facilities. So what they did is they had these sheep and dog bones. They sanded them. They had taken them from animals that had previously died. They made them into pins small enough to be inserted into the pigeon's humeral bones. This is the wing bone closest to the bird's body. And after 32 weeks of observation, that's a pretty long period of time, pigeons with sheep or dog bone pins were able to fly as well as before the operation. That is unheard of in broken bird bones. That is insane, and I love it. The other cool thing, you would think maybe taking something from a sheep or a dog and putting it in a pigeon, there might be rejection issues. There were no rejection issues in any of the implanted bones in this project.
Huh.
Yeah, so they're already starting to apply this into clinics in Iran, trying to do this with the larger birds, eagles, owls, seagulls. They're also, this is the next step, they're trying to take cattle or horse bones and shape them into plates to compare them to conventional metal plates for other types of rehabilitative bird surgeries. And I was talking to somebody about this a little bit ago, and they said, well, does this mean humans could get this someday? And yes, absolutely.
Instead of having, that's what I was just thinking. Instead of having metal, why not? Especially since it's reabsorbed, and maybe if you're going to heal, that's amazing.
Yeah. So of course, on one side, I was super duper excited about this because of how tough it is to rehab animals that fly. It's so hard. And so this is a huge leap forward in that, but also this huge potential for application across the animal kingdom from this, especially if you're going mammal to bird right now. That means mammal to mammal should actually be pretty simple.
Yeah.
So there you go. A little bit of exciting news related to injured birds in the wild.
I love it.
Yeah, and moving from injured birds to scared birds, I have a story from the University of Cambridge looking at Galapagos finches. So we were just talking about Darwin in the first half of the show and some of his theories and things like that. One of the things about Darwin that I always think is so funny is that I guess he really liked to eat a lot of the animals that he studied. That was one of the things. And so I always picture that, especially when they were talking about how finches first responded to Charles Darwin in this story in the Galapagos Islands in 1835 when the beagle came over. He could famously get close enough to throw his hat over the finches. They were so unused to humans, they didn't see Darwin, who could be a potential predator, as a threat. And since then, the arrival of humans and invasive predators like cats and rats on the islands has changed these birds' lives quite a bit. So on some of the islands, there are introduced predators. On some of the islands, there are lots of humans. And on some of the islands, there's not much. It's still pretty similar to how it was about almost 200 years ago. So this study is actually looking at what is happening to the birds who have introduced predators on the island, but more importantly, what's happening to the islands where they successfully eradicated the predators. They were looking at anti-predator behavior. So this is a fearful response to something that could eat you, which could be as simple as flying away or being wary. So that can have impacts because whether or not they're actually in fear of being eaten and whether or not they're actually in danger of being eaten, the time that they spend being spooked by fleeing, whether they're in danger or not, could better be spent looking for food, looking for a mate, laying eggs, tending to eggs, raising young. So all of those things can impact their survival and their, I guess you could say, fitness, if you're talking about kind of how selection is going to drive the way the finches act in the future. So what they found was that this anti-predator behavior, this kind of spook that they had when they got, they had an introduced predator on the island, sustained multiple generations after eradication of the introduced predators. So they were not afraid of anything. Then people came and they brought cats and all sorts of other stuff. And then after we removed the cats from some of the islands, they are still scared of everything.
Oh my goodness.
So see what cats do.
See what cats do.
See what cats do. So some islands have never had invasive predators. Others currently have invasive predators, domestic cats and rats. Others have had these predators in the past, have been eradicated. So the islands where they've been eradicated, they've been gone 8 or 13 years.
That's a long time.
Yeah, but this anti-predator behavior has been maintained. So yeah, it's an extra wrinkle when you're thinking about species management and protecting animals that are impacted, especially by human forces, whether it's us or other introduced predators. But knowing that their fear response could be on par with animals that are currently dealing with these predators, even 13 years after that, impacts how we anticipate how a species can respond after we remove that threat. So understanding the effects of human influence, like the introduction of invasive species, could help predict how species respond to rapidly changing environments. So that means this has to be part of the conversation, is that the negative impact of that could last for generations.
Yeah, I mean, what I'm imagining is that animals that behave in a more fearful manner, the ones that hide their nests, the ones that do evasive behaviors, or that run away from predators more often, those are the ones that survive when you have the invasive predators. Those then are personality types, genetically based, that
So this is a reversed foxtrot study.
Right. Yes. But then those are, I'm saying personality types, but those are genetic instructions that get passed down to the young. And so then you have populations that are made up of, not more aggressive, but
Scaredy cat.
more fearful.
Scared of cats.
All
Scared
the
of
friendly
cats.
birds got
Yeah.
eaten.
Yep. All the friendly birds got eaten.
Exactly.
Exactly. So how long will it take? And so I think that's an interesting, how long will it take with no invasive predators for individuals who have more friendly traits, the genes that lead to that, to make up a larger percentage of the population again?
Absolutely.
Yeah.
And there's this whole other crazy thing, which I'm not even going to get too far into, which is that some of these islands are also more urban than others. And on the islands that are more urban, they found that the quote unquote urban finches were more bold than those on the islands that had never seen invasive predators at all. So the presence of humans somehow made them bolder. So that's a whole extra
Interesting.
layer of confusing impacts of human fingers in the evolutionary pot, I suppose. But so
Stirring all
yeah,
the pots.
there's all sorts of stuff happening with these finches. It's the beauty of the Galapagos finches is that they're all these little tiny microcosms, and they move so quickly in evolutionary time. But it also means they could be in trouble.
Yeah. Oh, yeah. Wow, that's an interesting study. It comes down to something that, when you think, oh, what invasive, whatever, oh, birds are afraid of cats, fine. They learn to be afraid of cats. But when you think about it, I think it goes much deeper than that.
Yeah. And you
Very
can't just get rid of the cats. It's not that simple.
Yeah, actually it is.
No.
You can.
I
That's
mean,
the
it's a
first
good
step.
step one. It's a good step one. But part
Step
of the
one,
problem,
get rid of all
the
the
whole
cats.
point
Step
of
two, figure it out later.
the whole point of the research is that's
Get rid of
not
the
the
cats.
end. That's not the last step. You have to
The cats do
anticipate
lasting
You have
damage.
you have to anticipate
Just-
the lasting effects. Yeah.
just removing the predator is not enough.
You know what I immediately thought of? I thought of like I think is it Snow White? With the putting her hand up and the little bluebird coming and landing on her. If she had a cat, none of that. None of that.
I think actually
would
you're
have
thinking of Cinderella, and she did have a cat.
Is it Cinderella? Does she have a cat?
Yeah.
Cinderella
Cinderella wasn't allowed to have a cat.
Yes. So
Would have
moving
eaten
away
her horses.
from old fairy tales told by back to Disney again. We're coming full circle towards the end of the show here. Coming to the end of the show, we have a few more stories we want to get through very quickly. So I want to tell you on the bird front, staying on the bird front. Birds are getting smaller thanks to climate change, which is very interesting. Researchers looked at over 70,000 specimens from 52 North American migratory species collected over the last 40 years. So we're looking at several decades of change. They say that almost all the species were getting smaller, and interesting shift, even though body size, leg length was getting smaller, wingspan was getting longer. So these are migratory species. The birds with longer wings seem to be the ones that are surviving more. And they think that the smaller bodies might be helping the animals cool off more quickly. And so the trade-off between being able to have a body big enough to support migration and the metabolism that goes along with that, losing some of that size, is that they're able to withstand some of the warming temperatures they're up against a little bit better. But bigger wings. So there's a lot of changes happening to birds because of climate change, which is kind of crazy. And then, this other really fun study, dogs Dogs are able to understand words spoken by people with different dialects, from different dialects. So if you said had, had, but you said had a bunch of different ways, the dog would get that the word is had. If the dog knows the word had, the dog can hear the word had across these different dialects, knows it's the same word. They had a bunch of dogs with their owners when other strangers would say words to them, new words that they were just experiencing, would make the dogs perk up and pay attention. The dogs would kind of lose their attention as they were bored by the word being repeated, but in different accents. But then when somebody said a new word, the dog would pick up and get excited or interested again. The ears would perk up and then they would get bored again. So showing, this is what they say, that dogs can understand or follow phonemes between different dialects, which was previously considered a human-only trait.
Yeah. So in other words, they can understand words even if the articulation is rough.
I have some issues with this study. We can talk about it later, but it sounds like they're just recognizing a very different input.
Yeah, could be that as well.
If you want to test dialogues, I feel like you teach a dog to respond to a specific word to do a thing, and then have a bunch of different people say that word in different ways and see if they will still do that thing. Dogs are smart.
Yeah.
You can train them to voice commands, and then you can test that. I don't know.
Yep. Yeah. Anyway, what the big take home here, the researchers say, doesn't show the word that the dogs understand these words, but that dogs are listening to us.
For sure.
And which is
domestication.
Which is a dog training tip, Blair, seeing as you have a new puppy in the household, is, of course, to, before any command, say the dog's name. Because people talk constantly. So even though they're listening, there's a lot of blah, 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 blah to a dog. So you say the dog's name first, and they're like, oh, this one's for me. I got to pay attention.
Very good point.
Do you know how to teach a dog its name? I've been doing that with her.
You look at her and go, oh, who's a good puppy? Who's a good puppy? Your name is this. You say it like that.
It's all in the treats.
It's all in the treats.
Right here, it's eye contact. You give me eye contact, you get a treat when you hear this name.
And then do you do the same thing to yourself? You make the eye contact with your dog, but you put the treat in front of your face and you say Blair, and then you get to eat the treat.
Oh.
And then maybe the dog will learn that your name is Blair.
No. Speaking of dogs, I have a quick story about dogs as well.
Yeah, I know. Let's hear it.
So some people may have heard in the news over the past few days that an 18,000-year-old puppy was unfrozen in Siberian permafrost. The puppy still had milk teeth. It still had hair and whiskers and nails and eyelashes. It was very well preserved. And if you see pictures of this thing, it looks like a sleeping dog.
Wait, how old is it again?
18,000 years old.
18,000-year-old dog. Okay.
Yes,
it's not sleeping.
No, it's taking a long, cold sleep. It was under 2 months old, they think, when it died. It's so well preserved that they can get a lot of cool things from it. It looks kind of like a dog, kind of like a wolf. Since it's a baby, it's kind of hard to tell as well. University of Stockholm Center for Paleogenetics is conducting genetic testing on it, but they are not able to determine yet if it is a dog or a wolf. Dog or a wolf. The oldest known fossil of a domestic dog is about 14,700 years. But remains of dog-like canines are known from about 35,000 years ago. So there's an idea that dogs diverged from wolves around 36,900 to 41,500 years ago, right around 40,000 years ago. But so they should be diverged by now, these 18,000 years ago that this puppy came from, but they don't know if this is a dog or a wolf or a transitional form.
Okay.
But they're currently testing, I think it's DNA from a rib. So they're testing it, but so far they haven't really been able to figure out which of those it is.
So, yeah. What I'd be really interested in, especially where they found this pup, is to see if it is at all connected to Canis aurora borealis, the Inuit sled dog. Because there is evidence that the sled dogs throughout North America and in Greenland, the Inuits, those animals did not originate in those areas. That these animals have been brought with them throughout the sort of human expansion, and so the origin of that is it kind of looks like a husky, but it's not a husky. They have sort of wolf-like features as well, but it's not just a regular domesticated dog. It's its own separate breed of canine. And so I'd be really fascinated to see if there's a connection here with the Siberian 18,000-year-old pup and the origin of the Inuit sled dogs.
That would be very cool.
From what we know about how recently dogs and wolves diverged, and the fact that wolves and dogs can breed, but they do create sterile offspring at this point in time, I would not be surprised to find out that dogs have their own braided stream, a la hominids, because if people were bringing dog-like things in all over the planet at different points in time, then this can get kind of complicated, and it might not be a dog, and it might not be a wolf, and it might be something in between.
Mm-hmm. Dun, dun, dun. Transitional. Have we come to the end of the show, Justin? Do you have a story?
No, I've got 3 more stories.
Wait, what? They're not in the rundown.
Yeah, I know. I told you nothing's in the rundown. It's going in there later.
Okay,
I'm
quick.
working off the other rundown.
Okay, let's go.
This is fog for the future. Moisture farming, likely to be much more efficient, collecting freshwater in coastal regions than on Tatooine. But it is a thing that people do. There are coastal deserts where you don't have a lot of freshwater sources. So they have been for years using an engineering trick that is sort of back engineered from nature. They have these nets, these meshes that they are putting up that collect dewdrops from the fog, much like a spider's web might. This is Fan Cat Chan from the University of Illinois Urban-Champaign has figured out a new biometric fog gathering solution, this time using technology based on a desert beetle, which collect morning dew themselves, only they do it with an irregular morphology on their surface. Uneven bumps, flat areas on their backs that gather fresh water from desert fog or desert morning dew. So this is pretty fascinating. They've run some tests and they show that they can get more moisture from the air using this method.
Cool.
Very exciting. So let's see. According to the design was drawn from this fog interception methods used by trees that can typically collect about 53 gallons of water on an average day.
A lot of water.
From the original studies. And this is, an improvement on that idea. However, there may be a problem with that. So there might be it might be because the marine moisture fog brings comes with another little hitchhiker. This is research. No, researchers at the University of California, Santa Cruz have discovered elevated levels of mercury in mountain lions. So they decided to start to do a little bit of a deep dive. This is a neurotoxin that is not healthy. Concentrations of mercury in pumas in the Santa Cruz Mountains were 3 times higher than those that lived outside of the fog zone. Similarly, mercury levels in lichen and deer were significantly higher inside the fog belt than outside of it. What's interesting about the lichen is lichen doesn't have roots lichen is living off rock and is absorbing its nutrients from the atmosphere, not pulling them up from the ground. So it's not like it's a ground contamination thing so much. It is moving all the way up the food chain, though, from the lichen into everything else in the fog belt. So this is a normal, natural thing that happens when you have, okay, so mercury levels in the fog present no health risks to humans. So it's not like you have a dense mercury fog that you're going through. However, it's that whole food chain as things accumulate and accumulate and accumulate and build up into that food chain within the fog zone forests and areas. That's creating a concentration that ends up 1,000 times greater by the time you get to the mountain lions. And so this is, I guess, a normal result. It's methylmercury can survive the evaporation from ocean waters and travel through the fog to then be recollected in this manner. And then in the final study, I will run through real quick. This isn't actually a study. This is more sort of a science-based news thing. Editors-in-chiefs of pretty much every major scientific publication wrote a letter together. The editors-in-chief of the 6 major scientific review journals wrote a letter together about what the EPA is proposing. And while on one hand, it sounds like a transparency in science sort of a thing, where we want all of this information to be made public. One of the downsides to what the EPA is currently proposing in this new legislation is that the only things that they could make decisionable as the EPA are those things that are completely transparent studies. The problem with that is a lot of studies are done based on medical individuals' medical histories being combined. And that information cannot be made completely transparent because it's individual privacies. Plus, there are studies that are done that may have non-disclosure agreement, that sort of thing. These might be chemicals that you can't completely disclose. We ran into this thing, if you remember, a while back with fracking. Part of the problem was like, what is fracking doing in the environment? We can't tell you. Why? Everything that's in fracking, in the solutions in fracking, is proprietary. So we can't tell you exactly what's in it. Otherwise, we would be giving up our right. So it's but what this would do, according to the editors-in-chiefs of the 6 major scientific review journals, is even potentially retroactively make conclusions that the EPA has gotten to based on science to preserve human health, regulations that are there to protect us. It would make all of that unusable as a reference for the EPA, and therefore unwind tons of studies that have been done using people's individual medical histories and experiences as part of it. So it's EPA is under attack currently by, it seems, the EPA.
Right. But not in a good way. This is like hemorrhaging from within.
Yeah. It also means that any changes to regulation that would be under this new rule would automatically have to only use the available completely publicly transparent studies. So nothing based on human health histories that were gathered, even I think through metadata, which is, it gets
epidemiology.
Really
who needs it? Yeah. Want to know about cancer incidences? Can't use that.
Nope. Yeah. Let's ignore science when making these decisions. Is sort of what this is saying.
Wow. So if I get this straight, even if health information has been, all of the personal information has been scrubbed from it, and it's just numbers of certain types of cancers in certain locations in a database, that cannot be used because it's not where that data came from. It's not completely transparent.
That basically, the way this thing is written, that's correct. Yeah.
Wow.
And it feeds into okay, we won't get into the political, but there is like a conspiracy, like there's deep state thing that we hear about in the politics. These conspiracy theories. There's a deep state science thing where that stuff is just all made up. If you can't see every detail of it, you can't trust. It's attempt to throw shade at things that people don't want. Is by saying if we don't have every detail of the study, how can you possibly allow us to review it?
How can we make a decision based on that? Yeah,
even if parts of the data are completely inconsequential, or in this case, proprietary or private data that can't be made completely 100% transparent throughout every increment of it, it's then therefore not going to be able to use. Which at some point, that gets like if you really start to think about this, like. How much are they? How much is 100% transparency in this? Like, are we talking about the field notes taken the day of while the researchers were doing it, as opposed to the paper that they wrote? Like, where do you draw that line then?
Yeah.
On that 100% transparent full? And it means you could probably in a legal environment, which is not scientific at all, in a legal environment, you could probably get rid of any scientific study you wanted to.
Yeah, if it's interpreted in a particular way. Yeah. Oh, that's leaving us on a high note. Oh. I'm just gonna think. Jingle T-Rex, jingle T-Rex, jingle all the way. Right. The T-Rex comes with tiny arms and the people run away. Hey.
Oh, good.
There we go.
Wait, we're supposed to run?
Oh my God, we're coming to the end of the show. It's December, everyone. Right now, this is the first week of December. If you've made it this far to the end of the show, you're dedicated to TWIS. And I hope that you will take some time in the next couple of weeks to help us come up with our top 11 science stories of 2011. That's right. If you want to help, send me an email, or you can send us your ideas on Facebook or on Twitter. Like, that's hashtag top 11 science. Let's figure that out. We have a couple of weeks to put it together. And do you know what else is coming?
What's coming?
The end of the decade.
Oh my gosh.
So if anybody out there is interested in helping us go back through the last 10 years of TWIS for a special decade in review show, we'd appreciate your help. Let us know moments in TWIS's decade of history. We go further back, but are there moments that you like the best? Let us know what shows, what moments, so we can maybe compile some thoughts. It's a video. I don't know. We're thinking about it. So help us out. If you're interested, send me an email, kirsten@thisweekinscience.com. We're going to talk about it a little bit more in the after show, I think, here. But now it's time. Are we done? Did we do it? We did it. It's the end of the show. Thank you, everyone. It's time for shout outs. Thank you to Gordon Cloud for helping manage that chat room of ours. Fada, thank you for your help doing chat room stuff over on YouTube, social media, show notes. I appreciate all the hard work you put in on that. Identity 4, thank you for recording the show. And thank you to our Patreon sponsors. Thank you to Paul Disney, Ed Dyer, Andrew Swanson, Craig Landon, Andy Groh, Ed Stu Pollock, Philip Shane, Ken Hayes, Harrison Prather, Charlene Henry, Joshua Fury, Steve DeVell, Alex Wilson, Tony Steele, Richard Porter, Mark Mazzaros, Jack, Matthew Litwin, Jason Roberts, Bill K., Bob Calder, Eric Knapp, Richard, Brian Condren, Dave Neighbor, Taylor P.S., Josiah Zahner, Howard Tan, Donald Mundis, Sarah Forfar, Dan K., Matt Bass, Darwin Hannon, Patrick Pecoraro, Ben Bignell, Gene Tellier, John Gridley, Corinne Benton, Adam LaJoy, Sarah Chavis, Rodney Lewis, Tiffany Boyd, John Bertram, Mountain Sloth, Seth Gradney, Stephen Albaran, John Ratnaswamy, Dave Friedel, Daryl Myshak, Paul Ronovich, Sue Doster, Dave Wilkinson, Noodles, Kevin Reardon, Christoph Zucknerek, Ashish Pants, Ulysses Adkins, Artyom, Rick Ramus, Paul, John McKee, Jason Olds, Brian Carrington, Christopher Dreyer, Lisa Suzuki, Jim Trapode, Greg Riley, Sean Lamb, Steve Leisman, Kurt Larson, Rudy Garcia, Marjorie, Gary S., Robert, Greg Briggs, Brendan Minish, Christopher Rappin, Flying Out, Aaron Luthen, Matt Sutter, Mark Hessenflow, Kevin Parachan, Byron Lee, and EO. Thank you for all of your support on Patreon. If you...
I'm still amazed that you can get through that whole list with only one inhale at the beginning. There's going to be a point. There's going to be a point when we have so many Patreons that you will just pass out at some point going through this list.
I hope.
Yeah, Josiah Zahner. Somebody in the chat room was pointing out. Yeah, it's that Josiah Zahner. I think is he new to the Patreon fold?
He is new to the Patreon fold. It's pretty awesome.
Friend of the show for a long time, but yeah.
Friend of the show. That's right. Be a friend of the show. Be a friend of the show. Patreon. You can find information, that Patreon link at twis.org or patreon.com/thisweekinscience. On next week's show, we are going to be talking about some fun stuff related to Native American peoples of the Pacific Northwest, archaeological finds of the Pacific Northwest, the history of the region. Very much looking forward to it with a researcher from Portland State University named Virginia Butler. Really looking forward to that. And I think it's also Justin's birthday.
Mm-hmm.
Oh, that's perfect timing. Oh, that's very sweet. Thank you.
That's right. Archaeology for Justin's birthday.
Yay.
Once again, we're going to be broadcasting online live at 8 p.m. Pacific time at twis.org/live. Also YouTube and Facebook now. You can watch and join the chat rooms. Don't worry if you can't make it. You can find our past episodes at YouTube, Facebook, or twis.org.
Thank you for enjoying the show. TWIS is also available as a podcast. Just Google This Week in Science anywhere you can Google things. If you enjoyed the show, remember to tell your friends. If you did not enjoy the show, but you made it this far, you probably did enjoy the show.
Yeah. For more information on anything you've heard here today, show notes are available on our website. That's right. Our website is www.twis.org. While you're there, hey, make some comments, start some conversations. Those conversations will be with us, the hosts, or with other listeners. And while you're there, order the 2020 TWIS Blair's Animal Corner calendar from my head to your wall.
Nail it to the wall.
Yeah.
You can also contact us all directly. Email Kirsten at thisweekinscience.com, Justin at twistminion@gmail.com, and Blair at blairbaz@twis.org. Just be sure to put TWIS, TWIS, somewhere in your subject line. Otherwise, what will happen to your email, Blair?
Spam filtered into oblivion.
You can also hit us up on the Twitter where we are at TWIS Science, at Dr. Kiki, at JacksonFly, and at Blair's Menagerie. We'll love your feedback. If there's a topic you would like us to cover or address, a suggestion for an interview, a haiku that comes in the night, please let us know.
We'll be back here next week, and we hope you'll join us again for more great science news.
And if you learned anything from the show, remember,
it's all in your head.
This Week in Science. This Week in Science. This Week in Science. This Week in Science, it's the end of the world. So I'm setting up shop, got my banner unfurled. It says the scientist is in, I'm gonna sell my advice. Show them how to stop the robots with a simple device. I'll reverse global warming with a wave of my hand. And all it'll cost you is a couple of grand. 'Cause this week's science is coming your way. So everybody listen to what I say. I use the scientific method for all that it's worth. And I'll broadcast my opinion all over the earth. 'Cause it's This Week in Science. This Week in Science. This Week in Science. 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 This week in science. This week in science. This week in science. Science. I've got one disclaimer, and it shouldn't be news. That what I say may not represent your views, but I've done the calculations and I've got a plan. If you listen to the science, you may just yet understand that we're not trying to threaten your philosophy. We're just trying to save the world from jeopardy. And this week in science is coming your way. So everybody listen to everything we say. And if you use our method instead of rolling a die, we may rid the world of toxoplasma gondii. Cause it's this week in science. This week. I've got a laundry list of items I want to address. From stopping global hunger to dredging Loch Ness. I'm trying to promote more rational thought, and I'll try to answer any question you've got. But how can I ever see the changes I seek when I can only set up shop 1 hour a week? This week in science is coming your way. You better just listen to what we say, and if you learned anything from the words that we've said, then please just remember it's all in your head. Cause it's this week in science. This week in science. This week in science. Science. This week in science. This week in science. This week in science. Science. This week in 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 science.
I'm having no fun. It's the end of the show. It's the after show. We're after the show. You have a dog. We have a calendar. I have a calendar.
You have a calendar. I can't wait for my calendars. Did they arrive today?
Yes. Well, they arrived a little earlier, but I was not home to pick them up until today. So we'll get them today. Got the calendar.
They look good with the species names on there. It looks good.
They do. Yeah, I like it with the species names.
Yeah, people don't have to tweet at me asking what things are anymore.
Who is this, Blair? Well,
that's a booby.
This is a booby.
Yeah.
It's a blue-footed booby. Otherwise known as Sulanabuxii, something like that. Is the dog available in the Zazzle store? Nope.
No.
Yeah. Sorry about my sound cutting out again. My brother did some updates of drivers and tried to make it all fixed, and it seemed worse tonight than it has been in the past 3 times. But we did have a very long show, so yeah. What's down there? You looking at the dog again?
Kind of like, yeah. I'm trying to
Your dog down there. Your dog down there. Where's dog down there?
There's a dog right.
I don't see a dog. Oh, there she is. Hello, puppy.
She's on my lap.
She's so cute. Baby corgi. Noodles ordered 2 calendars. Awesome. Ooh. Yeah. What would be the file type that you would need to import the TWIS holidays to the calendar on your computer? Like, make it a Google calendar. But
yeah, I don't know.
I mean,
I don't know.
Yeah, I wonder how we'd do that.
I don't know, huh, Sadie? I don't know.
Recreate the 1920s. I'm not trying to recreate the 1920s. Interesting comments we get on the YouTubes sometimes. Yeah. Oh, yes. Blair is just waking the puppy up. That's it.
No.
To say, look, Sadie, here's my TWIS family. Look, Sadie. Hey, wake up.
I
Come
had
be
to
on
take her
TWIS.
from Brian because it's time for him to go to work.
Oh.
So
Have a good day at work, Brian.
I think what you're referring to, Buddha's palm, has the quote, fools are going to try and recreate the 1920s.
What was that going back
I think
to?
that was in response to, it would have been during the EPA story.
Oh, yes.
So
that makes
the
sense.
reference
Yep.
is to
Yes.
let's start environmental policy back to a point before we had done science and had an industrial revolution, which exposed people to all sorts of harmful carcinogens, etc., without any knowledge of the effects. And so
We
taking
didn't know.
100 years of scientific knowledge and basically tossing it out.
Mhm.
That was a very astute.
That's a very astute comment then. I get it. I get it. now.
context is everything.
Context is everything. Thanks for giving me some context, Justin.
Uh-huh.
Yeah, so okay. Right now, of course, I never have the calendar with me when I want it. Gosh darn it. I don't have what I need down here.
Yes, may I help you? May I
I
help you?
mean what I say, and I say what I mean.
You an upside down nugget?
Okay. As it stands for the holidays, we have the 25th and the January of the 1st not doing shows because of the holidays.
Mhm.
Yes. Yes, we do. Now, the 18th, we have scheduled as our TWIS Top 11 show. Justin, why are you having an earthquake?
No. Because I'm in a 7-story building, which shakes a lot.
I know he left.
Oh, .ics. Thanks for the format, everybody. Can we do that from an Excel? I don't know. We could figure that out. Probably. Top 11 show, December 18th. Right?
Yes.
Yes. Okay.
Yes.
There is absolutely no way that I will be able to do the top 11 show and a decade in review show kind of back to back on the 18th.
That's a lot.
It's a lot. It's a lot of the top 11 show is one of the shows that takes the most work for me during the year.
Yeah,
It takes
same.
a lot of
I
reviewing.
always think it's
and-
going to take less.
And I'm like, oh, it's fine. It's fine. We got the show notes. It's gonna be good. Nope. Takes me hours. So here's my thought that we could do a show somewhere in between before I've left town. I don't know when I'm leaving town, but just so as I know I've got good internet connection and all that kind of stuff. So maybe the 22nd or 23rd. Or
if it's at night, yeah.
At night, yes.
Yeah. 22nd is a Sunday. Sundays are hard for me.
Yeah, I know. Yeah.
But I could
23rd
definitely do
is
the
a Monday.
23rd. I could do the 23rd.
Okay. And then that would be like a special episode that could be released there in the middle.
Double check before I commit myself. Let me look at my
Monday would be
calendar.
better than the Sunday.
Okay.
The 18th is the next show. Do we have a show on the 18th?
Yeah, that's
We
December?
do. It's a Wednesday.
It is a Wednesday.
Yeah, Hanukkah starts on the 22nd. Yeah, 23rd.
Are you traveling?
Yeah, that's travel day.
What?
The 18th?
You know Wednesdays.
I think the way it works, though. So here's the thing. I'm traveling the 17th. And so we're going that direction. I don't lose a day. Going the other way, it takes 24 hours to travel from the United States to Denmark. From Denmark to the United States, it takes no time at all. I don't
Literally.
it takes no time.
You're gonna be
I-
so jet lagged. Oh my gosh.
Yeah, but
Good
my
night, Fada.
jet lag that way might be fine. I'm not sure. I haven't done the math. I don't know what that means. It's still gonna be. Yeah, it'll still be 5 a.m. to me, regardless of what I do for a while. Yeah.
And if you have not slept at all because you've been traveling, that'll be awesome.
Well, it'll
Smack
be
your
just
head on
normal
this.
Justin then.
Silly pup.
The tired Justin is the best version. It's the one.
Filters
the
are
one the
off.
audience really loves.
Oh, you think so?
I think so. I think the wide awake Justin is the one they're like, he keeps talking. The tired Justin's like, yeah, so this happened and we're done.
Yeah, it'd be fun to have some top guests, huh? Oh, I don't think I've planned. I can't plan ahead enough.
That's enough of a show.
This
There's
week
enough
in
to talk
scheduling
about.
that you're tuned into. If you're just joining us, this week in scheduling, where we come up with plans for stuff to do in the future.
That's right. We will schedule things in the future. Yeah, a poll is easy. Yeah, well, but that again means there has to be a list that's created initially
for the top 11 of the year. So I thought I thought of something that we could do for the decade in review, which sounded easy enough that I could take on myself. Which is that we could just go through the top 11 stories of the year.
Yeah, from each year.
Each of the last 10 years and compare them. And then rank them based on that and say what story, and I could say it right now, global warming was in every single one of those.
Pretty much.
Yeah. I think there's some things, I think black holes might actually show up surprisingly high in this because it's been a big thing. A lot of, I think Neanderthals, just because I've pushed them so hard.
No, there's been a lot of Neanderthal stuff the last decade.
Of course, CRISPR. Yes. CRISPR, of course, will be on this list. But I think that would be kind of an easy enough task.
Talk about the Higgs.
Mm-hmm.
Yeah, Higgs is probably there sufficiently to make it for the decade.
Mm-hmm.
I learned what Higgs could be, wasn't, and was.
Artificial intelligence?
All during TWIS.
Artificial intelligence may have made this list. But it'd be kind of curious to go back over all of the top 11 stories. I suppose 10 of them. 9 of them?
Mm-hmm. It would be interesting. Yeah, the 11 stories, top 11 stories. And then what I think is also interesting is not just what appears on the lists, but the the weight. So what number, like where they fall each year. So top of the list, bottom of the list. Yeah.
Averaging at 2.7 on our list was yeah, okay. So I can handle that too. That's still some simple.
Yeah, poop is a thing too. Microbiome.
Poop. Yeah. It's probably at a 3.4 or 5.7. Let's find out, but we don't know. We'll find out. We'll take this list. We'll I'll combine it all into one list with how it ranked on average over those. But what if it wasn't there for a year? How do you take that one? So we'll figure.
That's a 0.
That's a 0.
Oh, but so you have. Oh, you're right.
Yeah, then it's anchoring it to a 0. That's tough. Oh, I'm being told.
Opposite. You have to give.
I'm being told it's fine by the calculating team here at the TWIS headquarters, Denmark says.
No,
we got it. No problem.
I have a solution. You rank them. You give them point values according to rank. So a 1 spot is 11 points.
Okay.
And a 2 spot is 10 points, all the way to 11. And then if they weren't ranked, they get 0. And then the highest scoring are the number 1.
Yes. So this does sound to me somehow like you're doing bowling math, but I think it will work. Yeah, I think this is how bowling scores are calculated, but I think that'll work. That'll be fine.
Sadie has told her how it shall be done.
She's crying for some reason.
Why are you crying, Sadie?
I think it's because she was sleeping in the dark with dad until he had to go to work, and now it's all bright.
Oh, I'm crying too.
I have to return a puppy pad before I put her down.
I'm so crying. I so cry. Oh, puppy bed. Lots of bug stories. There have been lots of bug stories. Gravitational waves. Yes, Gaurav. Yeah. Bugs and poop from the animal corner.
Oh, yeah.
Bugs, poop, and invertebrate sex. And
I think there'll be a
spiders.
lot of spider sex.
Oh, dear. Yeah.
A lot of invertebrate sex. Yeah. Will show up probably on that list.
Yeah,
Sadie is eating a Christmas octopus right now.
Oh.
So 10 years ago would have been
2010.
prior to Blair.
Correct. I'm circa 2012.
Yes. So we have 2 Blairless years.
Yes. It's true. I was the twinkle in your eye.
Oh, yeah.
I was a
There's no-
zookeeper without a plan.
You were. You're like, I don't know.
I totally was. I was like, I like animals. I guess I'm doing this right now. I don't know.
I'll figure it out. And you did. You are.
I'm figuring it out, and none of it's set in stone.
Mm-hmm. Yeah. And I don't know, unlike Ethan, I don't think you have to have a crisis.
No,
But
no.
I think you can make a decision to, I don't need to do this anymore if you don't want to.
Yeah.
Don't feel like you have like this hair. It doesn't want to do what the other hair, all the show. I keep putting it back. Stay hair in this hair. It's like, no, I'm going to do what I want to do. I'm going to have my own path. Sorry. Okay, so yeah, there are a couple of okay. A show that we could do, but I still think it would be good to do the decade in review show, give ourselves a little bit more time to put that together and do it a different day, especially if the 18th, Justin, you're going to be traveling back and potentially jet lagged, and just doing one top 11 show is going to be a challenge.
I like the 23rd. I think that would be fine.
Could we maybe do that?
So wait, okay. So I'm obviously I'm a little bit confused because scheduling is not a thing my brain does.
No, I know that. Yeah, we'll just make it
so. We're talking about the 18th is going to be the top 11 show. Yes.
Of 2019. Yes.
Of 2019. Yes. But we're not going to delve into the decade at all.
Mm-mm.
No.
That we're going to reserve for the following show.
Mm-hmm.
Which is as of yet unscheduled, because we were not going to do a following show, but we realized there's this decade thing happening. Yeah,
I don't know if so. I'm the only hesitance I have upon this would be that there could be enough similarity between our year in review show and the subjects that are covered in the decade in review show to an extent, right? Like,
I think it would be important to figure out how to differentiate them. Yes.
Yeah. Or combine them. And I don't know. But I guess it depends on how deep of a dive we want to do on this decade. That's what you're saying. Like, if we want to do a deep decade dive, it needs to be its own show.
Right.
Okay.
Yeah. If we want to do a deep dive, yes, it needs to be.
So then, yeah. Then
but
let's do the show after is the decade review.
But if we do a superficial calculation, like we can go back through and go, what were the top numbers? Give them the numbers, count them out. Oh, this is our average. Oh, hey, this topic was, it's number 8 this year. It was number 12 on average. Yeah.
Mm-hmm.
And then the prediction show would come
in January.
The
first show of January.
Which will be the 8th, I think.
Look, I have a calendar.
Yeah.
I tell you.
Oh, 7th? 7th.
The 8th. You are correct.
8th. Because the 16th is Sketchfest.
Yeah.
Mhm.
That's on a Thursday, isn't it? Yes.
It is on a
Oh, yeah,
Thursday.
that makes-
Yeah, so we're
Yeah.
skipping the Wednesday show that week, I think.
Yes.
Mhm.
And just doing the live Thursday show
Mhm. Mhm.
in San Francisco,
Mhm.
which Justin may not be
So,
able to come to.
Yeah, Justin, you have to be in the United States for that.
Oh, I will.
Okay.
Yeah, I'll be
Also, you're
stateside.
supposed to be in the United States in February as well.
I'll be stateside
Okay.
for the next few months. So
Okay.
For
from
Seattle.
Sketch through Seattle.
Okay.
Yes.
Great.
Right. Yes. So for people who want to know what we're doing, we're telling you now. San Francisco people, we're going to be at the SF Sketch Fest at Cal Academy of Sciences on Thursday, January 16th, live.
Tickets
We're
are
doing
on
it
sale.
live.
Sketchfest tickets are out, so
Yeah, tickets are on sale, so you
Pick up
can
your
buy your
tickets.
nightlife tickets now. I need to make a post, put it on Facebook, and do all that kind of stuff.
Mhm,
Got to do all these things. It's like this list of things, and I'm having issues
there's
attacking.
usually a Facebook event for Sketchfest Nightlife that Cal Academy makes, and we can just, or Sketchfest makes, or maybe they both. I don't know.
Yeah,
And then we have to just share it out. It's
we
like-
can share it. Say,
Yeah.
do this, people. Get tickets to this. Beyond that, then we'll be in Seattle doing podcast during the family days at the AAAS conference, February.
Valentine's Day.
Yeah, it's not quite Valentine's Day.
Isn't it?
It's-
I thought we were.
it's on
You're
Valentine's
right. It is.
Yeah.
We're doing two. One on Valentine's Day, and one on Galileo's birthday or Hippo Day on the 15th,
Yeah.
14th, and 15th. It's going to be great. We're going to talk about science. So those weeks, we'll see what happens with
Okay.
podcasty live stuff.
There
But
she is.
there's the animal.
Let's see her.
Oh,
And we see the animal in its natural habitat. It has
you
decided
talking about me?
to chew on a bone.
Yes, she's teething.
Mm-hmm. On a teething. Yeah, so we have some stuff coming up. It's going to be very exciting. Will the 15 show happen? What 15?
I think he means January. No.
No, because that's too many shows in 1 week.
That's a lot of things.
Oh, there's no
It
such
takes
thing.
preparation.
There's no such thing.
I
as
like
too
to
many
be
shows.
prepared. You want me to prepare 2 shows in 1 week?
Yes.
Boy,
We used to do this before you came along.
I know.
We did
but
2
it's
shows a
hard.
week. Kiki is looking at like she doesn't remember. That's how much work it was. Kiki has
But how
blanked
long were
this.
they?
What?
How long was each of those? Was it 2 hours and 12 minutes? Like
No,
tonight?
they were each an hour long.
There you go.
Hour.
I think it was it Tuesdays and Thursdays or Mondays and Wednesdays? Tuesdays and
like
Thursdays,
one
I
day was
think.
the interview day, and one day was the.
It was not. Yeah, I don't remember.
And the first one usually had an interview, and then
Yeah.
the second one usually didn't, as I recall.
We could move back to that format.
Okay.
Tape it all at once, but drop it twice a week.
Mhm.
You know?
Or we could break it down into half-minute increments that are contiguous. So as one leaves off, you go, "Oh no, what happens next?" You got to listen to the next episode
You
to
have
find
to
out what it
bittorrent
was.
the whole thing.
Then you've got to
I-
sit through and click another ad off if you're watching on the YouTube.
I will say my one of my favorite podcasts. They do a scheduled weekly drop on Mondays, and then they
Mhm.
sometimes, like maybe twice a month when it's really busy, have an extra drop on Thursdays. But it's not consistent. The consistent one is Mondays, and it always drops then. And then, you know. So there's lots of podcasts that do that.
We can do whatever we want.
Yeah.
We're a podcast. I can do what I want. Well, no, within reason. Oh, nasty weather in New York City. No, say it isn't so. And Hot Rod wants 3 shows in a week. Okay.
Okay, pay us.
Support our Patreon more. Yes. Yes.
Yes, please make it so I can do this for a living.
That would be really, really, really great.
All right. Sounds like we have a lot
plan.
coming up
the
on the show.
23rd. What?
So I think it's important that we all get our rest in preparation.
I think you have a day ahead of you. What
I
do you
have
mean?
a whole day. I'm going to take a nap
Oh, right.
in
Nap
like
time.
2 hours.
Yeah, after
Once
the
the coffee
wears
wears out.
off.
Yeah.
I knew it.
Yeah.
That's what happened to me.
We'll go way too early.
I can't go to sleep right now. Full coffee.
Anything going on? No, can't think anything. Okay, we just next week and top 11 shows coming up, which is very exciting. It's December. Oh my goodness, buy a calendar. Patreon. Happy.
Say goodnight, Blair.
Good night, Blair. Say good night, Justin.
Can't.
Good morning,
Good
Justin.
morning. Say good morning.
Good morning, Justin.
Good
night,
Kiki.
Kiki.
Good night, everyone. Thanks for watching again. Thanks for joining. Really great chatting with you all. And I hope you have a wonderful week. I'm so glad we've weathered all our Thanksgiving woes and we are back again. Yes. Yeah, so good. Have a wonderful night. Thank you, everyone. We'll see you next week. Oh, wait, I can't do that and hit the end broadcast button.